So a very warm welcome to our distinguished guests, speakers and participants on the second day of myself, Dr. Nidhi Chauhan, and I will be your host for today. Before we start today's session, I would like to express my gratitude towards you all who sincerely contributed to this event in order to make it a success. This would not have been possible without the support of each and everyone present here. Our today's session mainly focused on the role of nanomaterials in agriculture, pollutant remediation, and environmental sciences. With our goal to provide an insight into the world of nanotechnology with its application in building a better society. We have an amazing program lineup for you. Today, we are joined by some brilliant researchers from various fields, but all united with a common passion to bring about positive societal change through the nanotechnology. I would like to give a heartily welcome to Professor Amit Kumar, Professor Sanjay K. Dhakate, Professor Rohit Srivastava, Dr. Sampash Saha, Professor Vandana Luthra, and all the young achievers here at MIT. They all are the esteemed speakers who have agreed to share their work and knowledge to enlighten us today. This seminar, students will be able to identify their valuable places in their current research that need improvement and hopefully be inspired to pursue their solutions. I ensure the seminar will be profitable and the next few hours will be enjoyable and fruitful for every one of you. Now, I would like to invite Ms. Kirti Saxena to introduce our first speaker, Professor Amit Kumar. Over to you, Kirti.
Thank you, ma'am. Good morning to all of you. My name is Kirti Saxena, and I would like to welcome all of you to second day of this workshop on smart nanotechnology in societal applications. Our first speaker of this session is Dr. Amit Kumar from Central University, Haryana. Dr. Amit Kumar completed his MSc degree in chemistry from Maharishi Dayanand University, Rohtak in 2007, followed by PhD from Department of Chemistry, Maharishi Dayanand University, Rohtak, and CSIR, National Physical Laboratory, New Delhi in 2011. After a brief stint as a lecturer in the MIT University, Noida, he joined the Konkuk University at Seoul, South Korea in 2012 as a postdoctoral researcher. In 2015, he again moved to MIT University, Noida as an assistant professor and served till 2020. With total citation of 1147 and H-index 20, he has published 131 papers in peer-reviewed journals. Area of his research work involve high-performance solution processable antipolar organic field effect devices and phototransistor, organic metal interface in organic field effect transistor, synthesis and characterization of metal complexes for organic electronic devices applications, fabrication and characterization of solution processable polymer electronic devices, and fabrication of advanced organic electronic devices like OLEDs, OFETs, and organic inverters. Today's talk is on energy sustainability. So I welcome you, sir, and I request you to complete your talk in 45 minutes, followed by 15 minutes question answer session. The platform is all yours, sir.
Thank you so much, Dr. Kirti Saxena. First of all, I want to ensure that am I audible and visible?
Yes, sir.
Okay, good morning all. Good morning, Professor Officina sir. And I'm also very thankful to the MIT Institute of Nanotechnology for providing me the opportunity to interact with the researchers, those who are working in the area of nanotechnology. So as Madam has explained that basically I am from inorganic chemistry background, but did my PhD in material science. So I would like to connect my research with nanotechnology and for societal application. So let me, without delaying, because sorry for the delay, there was some technical issue at my side. So 15 minutes has already passed. So without wasting any time, let me share my screen and start my today's presentation. So is my screen is visible?
The PPT is not visible, but you have shared your screen, but PPT is not visible, sir.
Okay.
Now it is visible, sir.
Is it visible, sir?
Yes, sir. Go to the slideshow mode. It is visible, sir.
Again, there is some issue at my place.
Amit, there is no issue. You can continue in this mode also, if it's not possible. Amit, please continue with the same mode, not issue.
Okay.
Now it's fine.
Okay, okay.
Yes, it is fine.
So today I want to discuss about some of the organic molecular semiconductors which we have developed and used them in highly stable organic electronic devices for societal application. And these organic semiconductor molecules are highly ordered organic semiconducting molecules, and these molecules can be arranged and used to make various kind of nanostructures for the fabrication of highly stable electronic devices. So outline of my talk will be like this, that will discuss about first some of the introduction to organic electronic devices, then 2 to 3 terminal organic electronic devices, what was our approach for the fabrication of these 2-3 terminal organic electronic devices, then summary and acknowledgement. We know that before 2000, in 2000, the Nobel Prize was given to these 3 eminent researchers, that is Hagen, Serakawa and Kilnowski, for the development of conductivity in polymeric materials. So after the discovery of the development of conductivity in polymers, a new class of materials were started, and researchers have started thinking that there are a lot of material choices are there, because before that mainly the semiconductor industry was dependent on inorganic semiconductors. So in inorganic semiconductors, we have very limited number of choices of materials. But in case of organic electronic devices, in organic chemistry, we can synthesize, we can tune the material as per our requirement. So n number of materials are there. So material choice is large in case of organic materials. So after the discovery, the possibilities are open for, means new way is there to develop and design the organic semiconductors as per our desired applications. So there are various, because we know that if we develop any technologies, there are various pros and cons of the technology. But apart from the disadvantages, there are a lot of advantages of these organic semiconductors. Means semiconducting materials, organic semiconductor materials are, we have n number of choices. There are various kind of combinations are available, that by designing or simply by tuning the backbone of our organic semiconductor, we can tune the properties of the organic semiconductor as per our requirement. So we can very easily engineer the properties of the organic semiconducting materials as per our requirement. Then in comparison to inorganic semiconductors, organic semiconductors are soluble in organic solvents. Then various processable techniques can be used or can be employed for the fabrication of the electronic devices based on organic semiconducting materials. As we know that organic semiconducting materials are solution processable, so can be used in printing technologies. Like we can use in inkjet printing, spray coating, spin coating, and various kind of printing technologies. Organic semiconducting materials can be used for the fabrication of high performance electronic devices. Then we also know that organic semiconducting materials are biodegradable materials. So these materials, we can say that these materials are also environmental friendly. Apart from these various advantages, some of the disadvantages are also there, that these devices are very prone to oxygen and moisture atmosphere. So the long-term stability is still a critical point in the electronic devices. Those are based on organic semiconductor. But in today's world, researchers have achieved a very good stability and long-term as well as shelf lifetime of the organic electronic devices. Mainly the functional polymers are or functional organic semiconductor are having various advantages and various applications, like in organic field effect transistors, solar cell, light emitting diode, then in sensors, then various in optical and electronic applications, also in fuel cells or supercapacitors, polymer batteries, or organic semiconductor based batteries. Organic semiconductors are applicable. Then we will discuss, as I said, that we will discuss 2 and 3 terminal electronic devices based on organic semiconductor. So a very well known and is market readily available in the market. The 2 terminal electronic devices, organic light emitting diode. So in organic light emitting diode, we use the photoluminescence and electroluminescence properties of the organic semiconductor. Means the organic semiconductor which are emitting light in the range of visible spectrum can be used as an electroluminescent or emissive material in case of organic light emitting diode. So light emitting diode is a very simple but very effective structure. That in organic light emitting diode, when organic semiconductor is placed in between 2 dissimilar electrodes, and when we apply the voltage, the present organic semiconductor get excited. Means holes can be extracted and electrons can be injected. So when we extract the hole can be extracted from the HOMO of the organic semiconductor, and electron can be injected into the LUMO of the semiconductor, LUMO of the organic semiconductor by these 2 dissimilar electrodes. Those are anode and cathode. So as we discussed, my dear students, that organic light emitting diode is very simple but very effective structure. And when we introduce electron into the LUMO and hole into the HOMO, they form the exciton. Means the organic semiconductor is now in the excited state, and we use this property. And when these 2 charge carriers comes into the vicinity of each other, they form an exciton, and de-excitation takes place, and the light is equals to the band gap of that organic semiconductor is released by this organic electronic device, and we see the color emitted by that display or device. So this property means electroluminescence, means luminescence in the presence of applied electric field is used. The property of electroluminescence of the organic semiconductor is used to fabricate two-terminal organic electronic device, that is organic light emitting diode. So in order to improve the properties, means efficiency of this organic light emitting diode, various structure can be optimized. We know that with respect to the means positivity of this organic semiconductor, there are some limitation with organic semiconductors also, that organic semiconductors cannot transport both kind of charge carriers simultaneously. Means in one kind of organic semiconductor possesses one kind of property. Either it will act as very good electron transporting material, or it will act as very good hole transporting material. So in order to improve the efficiency of these electronic devices for practical application, we have to improve their efficiencies. So in order to improve their efficiencies, we have to introduce other layers also in between these two dissimilar electrodes. So we will not go into the detail of this. So if any student is interested, they can interact with me separately. Then this is device operation. We have discussed already that by the application of electric field, introduction of hole and introduction of electron in HOMO and LUMO takes place. When they comes into the vicinity of each other, they form an excited pair, that is known as exciton, and de-excitation takes place and results into the emission of light. So for practical application, there are various kind of device structure, that is passive matrix, active matrix, transparent, top emitting, flexible, and white. So in laboratories, generally we fabricate passive matrix organic light emitting diodes. For practical application, we require active matrix organic light emitting diode. Then depending upon the properties and type of materials used for the fabrication of organic light emitting diode, if all kind of materials or layers are transparent, then it is known as transparent. Top emitting, flexible. Flexible displays are only possible with the help of organic semiconducting materials. For fabrication of flexible displays with inorganic semiconductors like silicon, germanium, and other arsenic is not possible. Then for full color display, we require white organic light emitting diode. Means the light can be used as a full color for the fabrication of full color displays. Because if white light is there, then with the help of filters, we can achieve or we can generate any kind of color. So for full color display, we require white organic light emitting diode. So there are various methods by which we can fabricate white organic light emitting diode. Like we can use multi-layer device structure, means the device in which different emitting layers are used to emit different kind of colors. For the fabrication of white full color display, we require three primary colors. Those are red, green, and blue. So if we combine these three primary colors, we can achieve white light. Then we can achieve the white organic light emitting white light by combining multi layers in the emissive layer of the organic light emitting diode. Means we can deposit three different layers which emits green, red, and blue color. Then second structure is stacked OLEDs. We can also achieve white light emission by fabricating stacked white organic light emitting diode. We can also achieve white emission using host guest system. Means if we combine the complementary colors in visible region, we can achieve white light emission. Then there are some of the characteristics of this white light full color displays or complete light white organic light emitting diode is color quality. Color quality can be assessed or optimized with the help of these three basic parameters: CIE coordinates, CRI, and CCT. Then device efficiency, quantum efficiency, internal quantum, external quantum, and power efficiency. Then improvement of the efficiency can be done by harvesting triplet state of the organic semiconductor, then optical doping, and we can also improve the efficiency by improving outcoupling efficiency of the organic light emitting diode. So we will not go into the detail of these properties, but just these are the characteristics and characterization of the white light emitting diodes. Means what are the properties and characteristics of our emitted white organic light emitting. So as we had discussed that various kind of device structures can be fabricated for the fabrication or for the achievement of the white organic light emitting diode. This is multi-layer. So we can deposit three different emissive layers, one over the other, in order to obtain white light from the device. Then second is stacked side by side or one on the other. Then third one is doping. We can dope the emissive layer with some of the efficient dopants in order to achieve the white emission from the emissive layer. So we have fabricated some of the white organic light emitting diodes in our laboratories by combining in this device structure, that is multi-layer device structure, and in doped structure. So in this layer, in this device, we used two different colors. One is in the range of like bluish greenish region, and another is in the range of yellow to orange red region. So by combining these two colors, we can achieve very good white organic light emitting diode. By optimizing the thickness and of these emissive layers, different color emitting layers into the emissive region. So you can see that in this case, by increasing the emission spectra in order to achieve the desired color of the light. So here we can see that by changing the position and thickness of these layers, this CI coordinates can be varied. So by tuning these thicknesses of these materials, materials in this device, we can achieve the emitted light's CI coordinates into the visible region, white region. Then second device structure we optimized by fabricating white organic light emitting diode by doping and complementary color in our emissive layer. So this kind of structure is known as host guest type of white organic light emitting diode. So in this case, what we did is we doped DCM dye act as a guest into the LiMeQ, lithium methyl quinolate, acting as a host emitter. And by combining these two, we can achieve the white organic light emitting diode. And in this case, the coordinates of this white light was very well within the white region, and that's were very close to ideal one, and those are 0.33, 0.33. So we can, in this there was various conclusions we drawn. In this, what we did is we used the localized doping technique to achieve white organic light emitting. So in this case, what we did is we localizedly doped this DCM dye within this LiMeQ layer. What we did is we deposit 10 angstrom, only 1 nanometer DCM dye in this layer, and we vary the depth of this DCM die from this alpha NPD, that is hole transporting layer, to the emissive layer interface. So at the depth of 10 nanometer, means 100 angstrom below, there were no contribution of this DCM die. And when we decrease the distance of this doping region from alpha NPD LIMEQ interface, we start getting the effect of this DCM into the emission spectra of this device. When we place this DCM die at the interface of alpha NPD LIMEQ, we obtained very good white light emission. Then, in order to further confirm that the emission is from both these components, we increase the thickness of this DCM at this interface. And we found that upon increasing the thickness, the emitted color of the lights starts shifting towards the actual color of the DCM dye, that is into the orange reddish region. Then from here, we conclude 3-4 things. One is this DCM dye layer was acting as a probe to detect that where the exciton is forming. One thing. Second, in our best device structure, in 1 nanometer DCM dye, the white organic light emitting diode was coming because of the incomplete energy transfer from host to the guest. Then we also analyzed and finalized that there is a Foster type of energy transfer. So mainly 3 things we conclude from this device structure, and these things can be used further for the fabrication of advanced electronics for practical application. And those white light was taking place in complete energy transfer from host to guest system. Second one is this DCM die was acting as a probe to detect the position of the formation of exciton into the emissive layer, and we found that the exciton was forming at alpha NPD LIMEQ interface. There is a reason why, because exciton can also be formed at this LIMEQ BCP layer. But in initial slides, I discussed that organic semiconductor can very efficiently transport either electron or hole, and fortunately this LIMEQ is a very good emissive as well as electron transporting material. So upon introduction of electrons and holes, before moving some distance by the holes, electron reaches very fastly because of the high electron transportability of this LIMEQ material. So readily availability of the electron, and because of the high energy barrier, electrons start accumulating here, and exciton form at this alpha NPD LIMEQ interface. So this probe, this energy transfer, because emission of light can be tuned by the introduction of this DCM layer. So this DCM layer, when we are moving this DCM layer towards this alpha NPD LIMEQ interface, contribution of the emission color emitted by DCM starts increasing. So it's and at this interface, when we introduce this layer at this interface, we got the contribution of this alpha NPD, this DCM dye in the emission color. Further to confirm this, we further increase the thickness of this layer here, and this confirms that the excitons are forming at this interface only. So these 3 main findings are very useful for the fabrication of advanced electronic devices for societal application, and these all are in nano range. You can see that the thickness of these, all the layers are in the nano range. So very finally we can design and tune the structure in the nano range of these organic fabricated organic electronic devices in order to achieve, in order to obtain the desired output from the fabricated device. And we can see that in the previous case, the CI coordinates were lying in this white region, but in this case, we are getting very CI coordinates very close to the ideal one, and those are 0.33, 0.33. These are some of the fabricated electronic devices in our laboratory. Then, wait for a second. Yes. Then we discussed that two-terminal electronic devices and three-terminal organic electronic devices can be fabricated by using organic semiconductors and by designing or means optimizing their nanostructures. So we discussed in case of two-terminal organic electronic devices, active matrix and passive matrix. Then for active matrix, we need the driving structure also. So if we want to fabricate flexible electronic device, then we need the flexible driving circuit also. So in order to fabricate the three-terminal electronic devices, we also developed some of the organic semiconductors and arranged them in various nanostructured forms in the active layer in order to obtain highly stable organic field effect transistors or organic field electronic devices. This is the this structure of organic field effect transistor. In this case, substrate, gate, gate electric, organic semiconductor, source and drain. So by tuning the properties of these organic semiconductor, we can tune the properties of the fabricated electronic device, that is organic field effect transistors. So there are various advantages of organic field effect transistors. Low cost processing because organic semiconductors are available, used, large area displays, then low temperature processing techniques, compatibility with plastic substrates, then applications are in OLEDs, e-paper, means in all the organic electronic systems, organic field effect transistors can be used. Then, as we discussed, transport either hole and electron, but cannot transport both the charge carriers at the same efficiency simultaneously. But in order to fabricate the practical organic electronic device for practical application, we required ambipolar field effect transistors. So in order to fabricate ambipolar field effect transistors, what we have to do? We have to structure and design, optimize the structure of the organic semiconductor layer, that is known as active layer in case of organic field effect transistors. So in order to achieve the maximum ambipolarity or balanced charge carrier transportability, various kind of this device structure, means active layer structure, can be optimized or designed in order to obtain the maximum efficiency. Just wait for a second, my slides are not moving, I think. Am I visible?
Yes, your slides are moving.
Am I audible?
Yes, yes.
Yes, sir.
Yes. So first one was the, see, so there are various potential issues in order to fabricate advanced organic field effect transistors for high efficiency organic electronic devices. One is charge injection, second is interface barrier modification for efficient energy in charge injection in unipolar, as well as charge injection in ambipolar OFETs. Then next one is channel formation and charge transportation in ambipolar OFETs. The major issues readily faced by the researchers in order to fabricate high efficiency organic electronic devices. So in order to address the injection issues, or in order to address the barrier between the electrode and the organic semiconductor, we modify this this interface by introducing the buffer layer of rubidium carbonate, or we can say that metal carbonates in case of organic effect transistors. In this device structure, we insert a buffer layer, means 5 angstrom, 10 angstrom to 20 angstrom rubidium carbonate, and it was charge injecting or electron injecting layer in between source drain and the organic semiconductor, means at the metal organic interface, and we obtained very good results in terms of device efficiency, mobility also increase, on-off ratio increase. Then we optimize the exact thickness of rubidium carbonate. There are we explained this by using XPS and UPS, that how this introduction of very buffer layer, means very thin layer, that is of the range of 5 angstrom, 10 angstrom and 20 angstrom, how the electron density, how the Fermi levels of the organic semiconductors are changing, and how they are improving the charge, how that reduce the charge with this potential barrier between the metal and organic interface, and how that this introduction of this buffer layer are improving the injection of the charges from metal to organic semiconductor.
Hello. Sir, we are unable to listen you. Is there any problem? Amit sir? Tanu ma'am, can we call him?
He's back. So let me call him.
We are trying to contact him. Please wait for 5 minutes.
Okay. I am.
Yes, sir. Yes, sir. Can you please
Okay,
share your
wait,
slide?
continue.
Yes, sir.
Okay.
Are you able to hear us, Dr. Amit?
Am I audible, madam?
Yes, you are, but your video is not turned on, as well as we're not able to see any slides.
Yeah, wait for a second.
Yeah, now your video is on.
Am I audible now?
You're audible, but you have to you've shared the other screen, actually, the screen of this meeting.
Is my screen visible now?
Yes.
So I was discussing about the active layer device structure in ambipolar organic field effect transistor. Wait for a second. So three kind of layers can be designed in order to fabricate high efficiency ambipolar organic field effect transistors for practical application. One is single component, second is bilayer, and third is blend structure. Is my screen visible now? Am I audible?
Yes.
Okay, so in single component device structure, one organic semiconductor is used for the transportation of both kind of charges, those are electrons as well as holes. In case of blend devices, bilayer device structure, we use two different organic semiconductors. One is P type and another is N type, one over the another. But we were discussing that in case of organic field effect transistors, charge transportation takes place by the introduction of charges from the source to the organic semiconductor, and the formation of channel takes place by the application of applied field at the gate. So gate biased tuned transportation takes place in case of organic field effect transistor. So by the application of the electric field, formation of channel takes place in between organic semiconductor and insulator interface. So in case of bilayer device structure, if P type of material is in contact with gate dielectric, then P channel will form at gate dielectric organic semiconductor interface, and the N channel will form at semiconductor interface. Again, there were problem of the injection, because we can tune the injection barrier as per the properties of the organic semiconductor. But in case of bilayer, if N type of organic semiconductor is in direct contact with source, then injection of holes becomes difficult in case of bilayer device structure. Then again, in case of bilayer device structure, obtaining high efficiency ambipolarity is a challenge and issue. Then similarly, we can fabricate the blend structure based active layer for the fabrication of ambipolar organic field effect transistor. Again, there are problem in case of blend device structure, because the different kind of device structure, organic semiconductor will act as an impurity for the counter charge carrier. So in order to address these issues, what we did, we create some nanostructures in the active layer. In order to address these issues, we designed and fabricate a new structure of active layer for ambipolar charge transportation. What we did, we prepare nanostructured layer of one organic semiconductor and deposit the another organic semiconductor layer and So in this case, what we make is we make um, microcrystals of P-type organic semiconductor using solution processable technique, and the semiconductor was tipped pentacene solution, and means different these crystals are formed, and over these crystals, what we did, we deposit N type of organic semiconductor. Then in this device structure, both the organic semiconductors are now in direct contact with gate dielectric. Then, by analyzing the structure of this device, we did the cross-sectional SAM of this device, and we found that when we did the cross-sectional SAM in this region, we found both the organic semiconductors in channel region, and when we did the SAM of this layer in this region, we found that in this region, both the semiconductors are there, and in this region, only F16 CuPC was there in direct contact with organic this gate dielectric. So alternate P and N channels are there. Alternate P and N type of organic semiconductors are in direct contact with gate dielectric, and we obtained very good V type of characteristics of this fabricated field effect device. We also fabricate the inverter, ambipolar inverter of this device, and we got the output in both the component, which is showing the ambipolarity, efficient ambipolarity of this fabricated electronic device. CMOS and NMOS is also there. Then mechanism cross transport is direct. In this case, both the organic semiconductors are in direct contact with organic semiconductor and the gate dielectric interface. So P channels are formed in this microcrystal.
May request to Amit sir, can you please conclude the session within 2 to 3 minutes? Thank you, sir. Sorry to interrupt you. Sir, we are unable to hear you. Amit sir. I think there is some internet issue. Ranu ma'am, are you trying to contact him? Yes, okay.
I've called him.
Yes, sir. Can you please conclude your talk? This, this way.
So madam, I will take 2-3 minutes only
Okay.
in order to summarize this. Am I audible?
Yes. Yes, sir. Yes, sir. You are audible. Please carry on, sir.
So these are the, I'm feeling very sorry that because of the network issue, I'm disconnecting again and again. Hello. Yes, now it is visible, audible, right? So am I audible, madam, now?
Yes, sir. Yes, sir. Please, sir.
So that was network issue. Sorry for the interruption.
No problem. Please.
I'm sorry, audience, because today, due to, I mean, there are various positive and negative aspects of this technology also. And I was feeling to be more, if we'll, in offline mode, like, but in online mode, there are some positive and negative issues, and we are facing the negative issues today.
Tanu ma'am, can we move to our next speaker? Okay, yes, I think it's platform.
So, as we had discussed about the device structure of organic field effect transistors in previous structure, only one, the limitation was that we addressed one issue, that is the formation of channel at organic semiconductor dielectric interface. But there was some issues that in that case also organic one kind of semiconductor was in contact with source and drain. So we address that issues in this device structure also, and we place both the organic semiconductors one side by side. Am I audible, madam, now?
Yes, sir. Yes, sir. Please.
So I'm concluding in 2 minutes only. Because of network, I am again and again facing the issues, and that is also landing you in trouble also. So these kind of things are really very irritating for me and the audience also. So I'm really very sorry, but that due to network issue, we are facing these kind of problems. So in this device structure, we place both the organic semiconductors one side by side, and we addressed both the issues. That in this case, both the organic semiconductors, we can see that both the organic semiconductors are in direct contact with source and drain, and both the organic semiconductors are in direct contact with our gate dielectric. So very efficient injection as well as very efficient charge transportation takes place in laterally stacked crystal based, microcrystal or nanocrystal based organic semiconductor field effect transistor. And in this also, we got the highest Hall mobility as well as electron mobility of 2.15 centimeter square per volt second, and very good rectification ratio also. When we convert this, when we apply this organic field effect transistors into electronic circuits like CMOS and RMOS systems. So we again fabricated, designed various kind of organic semiconductors, solution processable organic semiconductors that can be converted into various nano and micro structures for the fabrication of high efficiency organic field effect transistors. We functionalize our basic diketo polypyrrole based unit to convert them into the efficient organic semiconductors. So and we found we fabricate one organic semiconductor, that is the stability of that electronic device using this organic semiconductor was about even more than an year in ambient atmosphere. We apply those semiconductors in various electronic devices, and we found that their shelf life as well as operation life is very high. So by tuning our active layer into the nano and micro structure, we can fabricate very efficient, very stable organic electronic devices for societal application, or you can say that very efficient nanostructured organic electronic devices for various societal applications. So these are the conclusion, and thank you so very much for your kind attention. If you have any question, I can take the questions. Am I audible?
Yes, sir. Yes, sir.
Yes, sir.
Thank
you so much, sir.
Yes. Yes, please.
For this wonderful and informative talk. There is a question in chat box from Shringika Soni. Thank you, sir, for wonderful talk. I have one question. How do you think inorganic nanoparticles hybrid OFETs can change the characteristics of the device, and what parameters need to be optimized for better results?
Inorganic, what I understand from your question is you are asking about that how inorganic nanoparticles, right?
Yes, sir. Inorganic nanoparticles in hybrid
Inorganic nanoparticles can be used as a dopant, various kind of dopants in active layer in order to improve their properties, like N-type or P-type, or like ambipolar charge transportation, or you can say that improve the functionality of these organic semiconductors. So can be used as a dopant in case of organic electronic device layer to improve their efficiencies. Like I have used this rubidium carbonate also as a buffer layer, nanostructured layer, only 10 angstrom, 5 angstrom. So there were nanostructures of these rubidium carbonates were there, and they were acting as an means in charge injecting layer at the interface. And by the doping of these inorganic semiconductor, because in case of inorganic nanoparticles, charge carriers are concentrations are high. So we can transfer the concentration of these charges into the organic semiconductor. Thereby, we can tune their we can tune their Fermi levels, right? So extent of doping can be improved depending upon the nature of the organic semiconductor. We can also tune their channel charge transportation properties, right? So can be used as a dopant in case of organic semiconducting layer in order to improve their efficiencies.
Okay, thank you, sir.
So I think there is no more question. So let's thanks our speaker. Thank you, Amit sir, for the wonderful insight on the potential application of sustainable energy resource. Everyone here has an idea how difficult it is to design optoelectronic devices with negligible noise. Your depth knowledge of physics aspects on polymeric nanomaterial based organic field effect transistor and other electronic devices surely increase curiosity among the audience. Thank you once again, sir, for sharing your experience with us.
Madam, I am really sorry for.
No, we understand, sir.
I'm not happy because there are some like I'm sitting in a very remote area of Haryana. Actually, that is in Mahendragarh.
Yes.
And these days, holidays are there. So there is, हमारा जो यहाँ का जो network है, that is under repair, maintenance. So I'm using my mobile network only to connect this meeting. And I'm really very sorry for the inconvenience caused from my side, actually.
Really understand about this technical issues.
Thank you so much for your patience listening and bearing me in this condition. Thank you so much, madam.
Thank you, sir.
Thank you so much. Thank you so much.
Thank you, sir. Kirti, can you please invite our next speaker, Dr. Sanjay?
Yes, ma'am. Now I would like to invite Sanjay from Sanjay
Kirti, we are unable to hear you. Can you please speak a little bit loud? There is some problem. Yes.
Dr. Sanjay from RTM from RTM 1991.
Kirti, we are unable to hear you. Can you please check your mic? No. I think you can remove your headphone.
Hello, ma'am.
Yes, now.
Now I am audible.
Yes, yes, please.
You are audible, but I think you are using two devices simultaneously. Please check.
So I would like to invite our second speaker of this session. Dr. Sanjay R. Takate obtained his MSc from RTM Nagpur University in 1991.
Kirti,
Yes, ma'am.
as sir said, you're probably using two devices. Your voice is echoing. or you move out of the room wherever you're sitting right now.
Hello. Hello, ma'am. Now it is clear.
Yes.
Yes. Sorry. Dr. Sanjay joined CSIR NPL as scientist B in 1992 in Carbon Technology Unit. Currently, he is senior principal scientist and head Advanced Carbon Products Group in NPL. Also professor of ACSIR. He is working on various forms of carbon material for structural, energy, and environmental applications such as carbon fibers, carbon and polymer foams, carbon-carbon composites, ceramic carbon composite, etc. He is handling various R&D projects sponsored by CSIR, DST, BARC, and industries as well as international bilateral projects. He published so far more than 110 research papers in various international reputed journals, more than 110 conference papers, and 7 patents in his credit. He has also uh, he has delivered several invited talks in various reputed institutes for popularizing the carbon science and technology. He is also a reviewer of different international journals. He is also co-authors of 2 books and authors of 3 books chapters. He is recipient of Advanced Material Letter Scientist Award in 2011, which received during international conferences on advanced material, Jinan, China. He is the recipient of JICA Fellowship, prestigious JSPS Fellowship, JSPS Bridge Fellowship of Japan government, and worked in Osaka National Research Institute, National Aerospace Laboratory, and the University of Tokyo for more than 2 years' time. He is also a visiting fellow to Queensland University of Technology, Brisbane, Australia. He is supervising MTech and PhD students in the area of material science. Title of his today's talk is Value Addition to Agriculture and Forestry Waste to Reduce Greenhouse Gas Emission through Torrefaction. I welcome you, sir. I request you to complete your talk in 45 minutes, followed by 15 minutes question answer session. The platform is all yours, sir.
Okay, thank you. I think all organizers. Just I want to share my slide first. Share screen. Entire screen. It is visible?
No, sir.
No.
Can you please share the screen?
Cancel just again one more time. Share. Why it is not coming?
Yes, sir. It is visible now. Yes. Sir, can you please unmute your mic? Sir, we are unable to see the presentation. Yes, sir.
Where is the problem? I'm audible or not now?
You are audible, sir. Please share it again, sir.
Okay. Now visible? My slides are visible?
Yes, sir, it is visible. You can continue, sir.
Yes.
Okay. So thank you very much for inviting me. So actually I have seen the title of your workshop, value addition. So I'm thinking what to talk. But then later I find out it is about the nanotechnology also. So I am just covering two aspects in this my presentation. One is nanofibers from waste biomass based biopolymers, and another aspect is the utilization of waste biomass for the conversion of biofuel, and that can reduce the greenhouse gas emission. Okay, so so again, I am from National Physical Laboratory. If you know everyone, I think you all people maybe studied you in high school. Okay, what is National Physical Laboratory? It is National Meteorology Institute of the country and responsible for maintaining national standard, realization of standard, establishment of the standard, upgradation, maintenance, and dissemination of standard to the industry for quality infrastructure and quality providing the quality life to the people of this country. So I'm starting with our nanomaterials. So nanomaterials are those which have structure component with at least one dimension. Means what I mean is length, width, or diameter. It is up to the level of 100 nanometers. Then we can call these are nanomaterials. So compared to conventional nanomaterials, the grain size between 100 micron to 1 mm, whereas in case of nanomaterials, particles with size between 1 to 100 nanometers are normally uh, regarded as nanomaterials. The average size of nanometer in order of 1 to 2 angstrom in a radius. So 1 nanometer is equivalent to the 10 angstrom. 1 nanometer there are 3 to 5 atoms. So means it is particularly when we are talking about the nanomaterials, that is we are talking about the atomic level. Whatever the means materials we are developing, that is on the atomic level. So two principal factors that cause the properties of nanomaterials compared to the bulk materials. When we are talking about nanomaterials from bulk material, we are reducing the size. When we are reducing the size, relatively surface area of that material is increased, and there is a quantum confinement. So this factor changes the enhance the properties such as reactivity and electrical characteristics of the material. And according to the again the surface effect, if you know a particle size decreases, greater proportion of atoms are found at the surface compared to those inside. So for example, a particle 30 nanometer size less than 5% of its atom on its surface. If size is 10 nanometer, then number of percentage of atoms on the surface increases. And again, further, the nanomaterial size, if you reduce the atoms on the surface increases, and that is up to 50% if the size is 3 nanometers. So nanoparticles are more reactive than the larger particles because of the high surface area. And the quantum effect, if you know, the quantum confinement effect can be observed once the particle size decreases, okay, from few nanometer, 100 nanometer to only few nanometers in the range of 5 nanometers. Then quantum confinement is responsible for increasing energy difference between energy state and band gaps. And this phenomena is tightly related to optical and electrical properties of materials. When materials are very small, their electronics and optical properties deviate substantially from that of the bulk materials. And if you compare and see if their gold particle size is reduced, so that color it changes. Okay, so if you see in the figure, means for initially just it is a violet and violet to then we are coming to the red when particle size of the gold nanoparticle is decreased. So that is the advantage of this nanomaterials. So again, classification of nanomaterials, one dimension, two dimension, I think you all people heard. So in one dimensional materials, you can thin film, surface coating, computer chips, two dimensional material. And in case of carbon nanomaterial, if you see the one dimensional materials, uh, there are different one dimensional materials, then two dimensional materials, carbon nanotube, bucky paper, two dimensional graphene, three-dimensional nanomaterials, nanoparticle, precipitate, colloids, and quantum dots. So I will talk today here a little bit about the nanofibers. So nanofibers are little bit different as compared to the nanoparticles and nanotubes. According to the definition of the nanofibers, as per the literature, it is a little bit different. For nanofibers, the definition is the nanofibers means length at least up to the length is maybe continuous, but the diameter vary from 100 nanometer to 1000 nanometer, that is up to the 1 micron. And if you see in the comparison, the if you see in the comparison in the photographs, how these nanofibers are very small as compared to the human hair. So human hair is again in the range of more than 20 micron, and if nanofibers are there, they are very, very small. Okay. So how we are producing this nanofiber? There are different techniques: drying technique, template synthesis technique, phase separation, and self-assembling and electrospinning. So electrospinning, I will talk about a little bit electrospinning. It is a simple technique. We have to spin the polymer solution by applying the high electric field. And if you see in the video, this by applying the high electric field, this polymer is oriented and polymer is positively charged, and they are spinning from the spinneret, and they are continuously that the fibers are coming from the spinneret and that's collected on the collector. So these fiber have very high surface area because these fibers are stacking on one another. So we will get mat type structure. So that having high porosity, then these fibers are continuous and having a high aspect ratio, highly oriented and crystalline because we are controlling the dimensions of the fibers. So they are crystalline, ultra thin, lightweight material, membrane like technology, and possibly to mix and soft touch. Very, very messy because these are nanofiber, polymer based nanofibers. They are very soft. So this is the electrospinning technique. We are synthesizing or drying the nanofibers. So this nanofiber processing is depend upon two important parameters, that is polymer solution property. Another is processing condition, and third is ambient condition. So polymer solution, what type of polymer solution should require for electrospinning? So that polymer solution, we have to see what is the molecular weight. We required molecular weight, high molecular weight, then concentration of the polymer, because we have to mix this whatever the polymer into some solvent. So that the polymer should be uniformly dissolved in the solvent so that we can get very good uniform solution. Then only we can able to spin the solution. Then again, the conductivity of solution is as one of the important factor, viscosity, surface tension, and solvent vapor pressure. Solvent vapor pressure means when we are drying the nanofibers from the spinneret and we are collecting the nanofiber from collector, during that means very few nanoseconds that our solvent should be evaporated so that fiber will be collected. If that solvent will be not evaporated during the processing, so we will not get the nanofiber correctly on the collector. So if you see in the figure, there is a electrospinning machine, collector is there are syringe pump upper side, and there are different three syringes. In that we have to fill our polymer solution and apply the high electric field, and by optimizing other processing parameter, we can process the nanofibers and it collect on the collectors. So basic principle of this again electrospinning. Electrospinning is a fiber production method which use electric force to draw the charged thread. The thread means fibers of polymer solution or polymer melt up to the fiber diameter in the order of some 100 nanometers. So again I told you it is max up to 1000 nanometers that fiber diameter in case of the nanofibers. So there are three different edges when we are putting this polymer solution in the syringe and we are applying the high electric field at the end of needle of the syringe, end of the syringe. So there are different types of mechanism is happening. One is jet initiation, jet thinning, and jet
Sir, you're not audible. Yakati, sir, you're not audible. Am I audible to you, sir?
Yes, ma'am.
Sir,
solidification. These fibers on the cylinder. So we will get somewhat aligned nanofibers on the cylindrical collector. But if we can
Yakati, sir, Yakati, sir.
so, yeah,
Sir, your screen sharing is not visible.
no, not visible.
No,
Slides are not coming.
no. Your voice was also gone. Now we can hear you.
Just a moment. Now, can you see the slides or not?
Not yet, sir.
Oh, whatever. Where is the problem? Again, I can try.
Sir, you have to share your screen. You've shared the, yes, now we can see.
You can see now?
Yes, sir.
Okay.
So please go to the slideshow.
Okay. Okay. It just
I think, yes.
okay now?
Yes, sir. Sir, can you do me a favor? One of the participants, there is a stop sharing tiny window at the bottom. If you could just press that hide button so that line is obstructing yours. Yes, yes. Thank you so
Okay.
much. Yes.
So I was on this slide means how we can get different types of fibers on different type of collectors. So when we have the stationary collectors, so that the fibers are coming from the spinneret and they are collected on the stationary collector, so they are randomly oriented. Whereas in case of the collector is cylindrical and that collector is rotating around some particular axis, so that fibers are deposited on cylinder and that fibers also move according to rotation, and they are collecting cylindrically on the collector. So in this case, we will get little bit aligned nanofibers. Whereas if the collector edge is very sharp, means very sharp, so that we can fix the fibers in that particular region, so that most of the fibers are going to align. So we will get the aligned nanofibers on the collectors. So these are the different means how these nanofibers are we are getting, because the this concentration of the polymer is very much important, and another aspect is electrical field, how much electrical field we are applying. So if the polymer concentration is less, then we will get just like the polymer is going to sprinkle on the collector. So we will get the just like the spray, not fibers are coming directly from the your spinneret. Whereas when increasing the concentration of the polymer solution, so we will get less amount of bits than we are getting the fibers. Okay, so it is very much important. We have to control the concentration of the polymer in the solution. Another thing is that we have to control the electric field also. If the electric field is less, we will get smoother fibers. Whereas when we are applying the electric field high, so we will get the rough fiber, and the fiber diameter also increases. So there are different type of application of these nanofibers. If you see here, there are three different sectors: energy, healthcare, water, and environment. So I will talk on one, two aspect of that applications. So here, Miss, just initially also I talked about, I am going to talk about the biopolymers. So my biopolymers, because if you know, our country has a lot of waste biomaterials, and from that waste biomaterial, if you see agriculture waste, forestry waste, or whatever it may type of waste, and particularly in case of agriculture and forestry waste, that plant biomass consists of three main component, major component, and that is cellulose, lignin, and hemicellulose. So cellulose is already means using from long time, that in the form of rayon for making the fibers. But again, that depend upon the yield, how much yield of that particular component is there. So it is very difficult. But nowadays, when we are extracting this cellulose, lignin, and hemicellulose, so there is a lot of work is going on to make these biopolymer based materials, particularly nanofibers, nanocrystals, and again different type of materials for different applications. So because these cellulose and lignin are most abundant biopolymers, and it is renewable polymers, so a lot of work is going on, and again from that polymer you can able to convert carbon into the carbon nanofibers, and there are a lot of application, because these materials are inexpensive, renewable, and high carbon content, and it is easily available, and most of this material we will get a byproduct from pulp and paper production, as well as by refining. If you see here the structure of this plant biomass, so there are three major components: lignin, hemicellulose, and cellulose. So lignin is more aromatic type as compared to other materials, and cellulose also. So particularly cellulose and lignin, they are using for making different types of nanofibers, as well as fibers, and nano crystals, and carbon into conversion into the nanomaterials, as well as quantum dots, as well as nano tubes, and so many things. So advantage of these nanofibers, uh, I just already I have spoken in this last slide, so I don't want to go here more. So here I'm just showing how we are making this cellulose based nanofiber. So again, if you can take the cellulose, it cannot directly spin. We have to make acetylation. So we have to convert cellulose into cellulose acetate, and then only it is going to spinable. It's very difficult to cellulose directly spin. So generally, whatever people are working, they have to convert this cellulose into cellulose acetate, and then we have to this cellulose acetate we have to dissolve in the some particular solvent. It may be different type of solvents are there, but we have to try that solvent should be again green, so it should not be impact on the environment. So in this case, we made the cellulose solution, so cellulose acetate solution, and this cellulose acetate solution is loaded on the syringe, and then nanofibers are get, and we will get the seed in the form of seed, nanofiber seed. And if you can observe by scanning electron microscope, so there may be fibers are oriented in different direction in the seed, but in naked eye you can see just like a paper. Okay, but there are nanofibers randomly oriented, and some are partly oriented in particular direction. So once we will get this nanofiber sheet, we can convert into the carbon nanofiber by two important process, that is stabilization. So stabilization is that again we have to means introduce some oxygen content in the structure of this cellulose, so that we have to this linear polymer is converted into cross-linked polymer, so that it may be stable for further processing. Mean that is different heat treatment temperature up to 1000 degrees centigrade and the inert atmosphere particularly. So if you see the morphology of this cellulose acetate nanofiber by scanning electron microscopy, so this figure A, B, and C, actually these are the means cellulose acetate nanofibers, polymer nanofibers at a different magnification. Okay, and when we are converting into carbon nanofibers, means first step is stabilized nanofiber. So in stabilized nanofiber is D sample. So if you compare these fibers of the same magnitude figure B and D, so after stabilization there is a little bit decrease in the diameter of the nanofiber, and when further we can convert the stabilized nanofiber into the carbon nanofiber, so fiber diameter further decreases. Okay, this shown in the figure E and F. So when we are carbonizing this nanofiber at different temperatures, so we have to study the structure of this nanofiber, and Raman spectroscopy is a very good tool to study this nanofiber structure at two different heat treated nanofiber, 800 degrees centigrade and 1000 degrees centigrade. So if you see here, we will get the what amount of defects are there. D is showing defect and G is sp2 content and sp3 content. So because these fibers are not heat treated to more than 1000 degrees centigrade, so there are a lot of defects that indicating by the D peak. So a lot of work we have done, and this work is published in cellulose acetate based nanofiber synthesis manufacturing and application. This is one of the book chapter published in Springer. So another application of this nanofiber we can make as a substrate for making the thermoelectric devices. So you know the what is thermoelectric devices? We have to convert thermal means heat into the electrical energy by PN junction. Okay, so in that case also generally we are using different types of material for making the thermoelectric devices. So there are two types of thermoelectric devices are used. That is generation of clean electrical power by employing thermoelectric generator using waste heat, and another is cooling application, that is air conditioning and refrigeration. So in that case also, if you can use the nanomaterials, so we can improve the performance of these thermoelectric devices. So particularly thermoelectric devices that we can say their performance is judged by the ZT, that is the figure of merit, and that figure of merit is depend upon particularly the electrical conductivity, thermal conductivity, Seebeck coefficient. These all parameters are connected to each other. So basically, when we are talking about the thermoelectric material, we should have high electrical conductivity and low thermal conductivity. So for that, if you can use the nanomaterials, so there are large grain boundaries when we are making the material. So thermal conductivity less there, but whereas electrical conductivity high. So these are the nanomaterials are very good for making the thermoelectric devices. So we are there are different means in case of inorganic thermoelectric materials, they are very rigid, heavyweight and expensive. So for that, people are trying to working on the organic inorganic based flexible thermoelectric materials. So if we can make the flexible devices that may be very easy to handle and easy to means operate also. So in that case, we are trying to working on the thermoelectric materials by using the nanofibers, cellulose-based nanofibers. So if you see here, again, we are making here cellulose-based nanofiber by taking cellulose acetate and it is making solution with some solvents. Then we have to mix properly the cellulose acetate in the solvent to make the proper solution. Then we will electrospoon, and if you see here, the sheet, white sheet, that is a cellulose acetate nanofiber, and it is a flexible. Okay, and after that, what we have done, we are putting the thermoelectric material B to T3 by magnetic sputtering, and that is deposited on the nanofiber sheet. So if you see here that electron spin nanofibers means micrograph that shows the nanofibers are oriented randomly, and when by this is magneton sputtering, when we are incorporating these nanomaterials, so they are deposited on the nanofibers uniformly, and we will get the flexible type of materials by using the nanofibers. So here again, if you see after means depositing this B to T3 on the cellulose-based nanofiber, there are micrograph. Initially, we have taken as such, and then after depositing the thermoelectric materials, and if you see here how this elemental energy showed, initially only there is a carbon and oxygen in case of cellulose acetate nanofiber, and when we are incorporating B to T3, then that showing deposited on the nanofiber, and that elemental analysis clearly evident that that fibers consist of carbon, oxygen, helium, and barium. So after making this material, we are study the electrical conductivity of that material, that is electron transfer property, and that is dependent upon how this means electrical conductivity increases with the temperature that is shown here. And this nanofiber are heat treated at different temperature, means 300 degrees centigrade, 400 degrees centigrade, and 500 degrees centigrade. And then we have studied the electrical conductivity. So with temperature, this electrical conductivity of this material is increased, as well as the Hall concentration and carrier mobility also increases with increasing the heat treatment temperature of the nanofibers. So another application means that I talked about the cellulose-based nanofibers. Now I am talking about the lignin-based nanofibers. So lignin is also very good source of carbon, and that having a higher means content of the carbon in the structure. So this is also very good, but it is again there are a lot of problems to spin these nanofibers only by high concentration of the lignin. So because due to the its amorphous nature. Okay, so there are different types of means approaches adopted by the research community, and ultimately we found that it is possible to means spin lignin up to 90% by utilizing solvent like DI water, acetic acid. So if you see here, we are able to produce lignin-based nanofiber by mixture of lignin and PVA, and lignin is 90%. So okay, so here is the process. We have to take on the crop lignin powder. We have to stir in acetic acid, and we will get lignin solution. And we have to take the PVA solution separately, mix both the solution, and we will get lignin PVA solution. And then we have to apply the solution in the electrospinning machine. Okay, so we have to syringe there and put the solution in the syringe, and we have to apply high electric field, and we will get the lignin based nanofibers. And then further we have to convert this lignin based nanofiber into carbon nanofibers by stabilization. Initial process is stabilization, then after stabilization different heat treatment temperature, that is 600 degrees centigrade, 800 degrees centigrade, and 1000 degrees centigrade. Then we will get different types of carbon nanofibers, but that fibers having different type of carbon content, because when we are heating at different temperature, the carbon fiber content is different, carbon content is different. So this, if you see here, uh, just I am showing you the morphology of these nanofibers, lignin nanofiber. Initially, if you see here in the figure A, and then after converting this nanofiber into the stabilizes into carbon nanofibers, that is heat treated to different temperatures, 600 degrees centigrade, 800 degrees centigrade, and 1000 degrees centigrade. So if you see comparatively, this diameter of these nanofibers are changing, and when temperature increasing, heat treatment temperature, the fiber diameter is decreasing. So initially, what we are getting, the fiber diameter is around 2000 nanometers. So, but we cannot say that, because in that case, again, I am telling you, here that fibers
Excuse
are
me, sir.
not circular.
Sir, can you please wind up in 2-3 minutes?
How much time?
Next 2-3 minutes.
Okay. Okay,
Thank you so
anyway, I
much.
will stop anytime. Then we will get different types of fiber, but here our fiber diameter means it is not cylindrical, but it is like a ribbon type of fiber. So that depend upon the our solubility of the polymer in the solvent, as well as the vapor pressure of this solution. Okay, so we are getting ribbon type of polymer, and then we have characterized these polymer fibers by Raman spectroscopy and FTIR, and measure the electrical conductivity. So when increasing the heat treatment temperature, that electrical conductivity of this nanofiber is increasing. And then we have to measure the surface area and pore size distribution, because these are the mats. It is not a single nanofibers, these are the mats in the form of paper. So we have to check what is the porosity level in this nanofiber sheet, and what is the surface area. So we measure the surface area and porosity. If you see here in the table, the porosity of surface area of the nanofiber is initially low, around 7 meters square per gram. But when heat treated to 800 degrees centigrade, suddenly that surface area is increases, but further heat treatment it decreases. And accordingly, that other parameter, that is total pore volume and average pore size, is also changing. So one of the application of this nanofiber we use, we made the electrode for supercapacitor application, and these are the different characteristics of the supercapacitor when we are measure by CV, cyclic voltammetry, and there are different current potential voltage versus current data. And ultimately what we are getting here, so again, these are different characteristics of electrochemical chemistry. I don't want to go there. So what is ultimate capacity we are getting here? If you see here, ultimate capacity, and this means nanofiber electrode is stable up to the 10,000 cycle, and this capacity retention is 99.5%. So this shows that this type of material is very useful for making the solid state supercapacitor devices. So this paper is published in materials chemistry and physics. So another aspect of these nanofibers, uh, in that particular paper, supercapacitor application, we have not activated this fiber. So in another study, we have activated this nanofiber and make activated nanofiber. So again, I don't want to go in all details. So again, after activation, this nanofiber is characterized by Raman spectroscopy, scanning electron microscopy, and BT surface area and porosity. So if you see here, as compared to earlier, when we are using nanofiber, cellulose-based nanofiber, carbon nanofiber, heat treated to different temperature, and after activation, if you see here the surface area, it is significant, very high. Hello. And then this is all electrochemical properties we are studied by cyclic voltammetry, and what I am just showing that here. So here three approaches we have adopted. One is carbon nano means activated carbon nanofibers, and another is the activated chopped activated carbon nanofibers. So if you see the difference in the specific capacity, so maximum capacity specific capacitance is given by activated carbon nanofibers. So these are all other characteristics. I don't want to go in detail. So this type of means carbon nanofibers are because these are flexible. So it is we can make the flexible devices by using uh, this lignin-based carbon nanofibers in the supercapacitor application. So here we are showing how this material, when we are bending at different degree, so how there is no any effect on the performance that shows from this slide after 1000 cycle. And this is same microgram. I don't want to discuss. So this work is also we have published in the Journal of Energy Storage, that is activated green carbon based 2D nanofabrics mats for ultra flexible all solid state capacitor. So that highlights of this study is activated 2D carbon nanofabrics by electrospinning technique by using biopolymer. It is a green precursor. It is a green technology, and that have low impact on the environment and high electrical chemical attachment as compared to powder. Means if you compare with powder nanofibers and sheet of the nanofiber sheet, and this flexible supercapacitor device shows stable performance in different bending mode, and it giving high energy as well as power density with high cyclicability. So anyway, means if you don't have time, so I will stop here because another component is different. So it is regarding to the nanomaterials. Thank you very much.
Thank you so much, sir. So there are few questions. First from Harshit. Good morning, sir. Very interesting talk. I have one question. In the nanofiber synthesis, what is needle diameter? Is there any correlation between pressure across the syringe and electric field with respect to fiber diameter? Hello. Hello, sir.
Sanjay sir? Are we audible? Sanjay sir?
Hello, I'm audible or not?
Yes, sir. Yes,
Yes,
sir. Now,
sir.
yes, sir. Please, sir.
So what is the question? Because in between there was not a network. I have not listen you properly.
Okay, sir. So the
So
question
I
was,
think he's asking about the needle diameter. Okay.
yes, sir.
So that is about zero point 0.5 mm. Okay.
Okay, sir. And second question is from Shringika Soni.
Uh,
Sir, did you check structural and chemical stability of nanofibers made up of biopolymers in terms of time and external factors?
uh,
And can we
okay.
use other polymers such starch? If no, then why?
So the starch. First, I will take about the starch because starch having a very small molecular change. Okay, so we should have the very good molecular weight, and that particular starch, whatever it may be soluble and particular solvent, as well as we require the conductivity also. Unless there is not conductivity, if molecules are very small change, so we will not get conductivity. Then it is not spinnable. Another, I think he is talking about the stability. Okay, see, as such, a polymer are not stable to all the environment. Okay, but when we are converting these biopolymers into the carbon nanofibers, okay, so carbon nanofibers are stable in chemical and all other environmental conditions.
Okay, sir. So next question is from Jaslyn. Good morning, sir. Thank you for a wonderful presentation. I am just curious, what is your source material in extracting cellulose nanofiber? Did you experience agglomeration on your nanomaterial as you isolate cellulose nanofiber?
Did you experience agglomeration? So actually, we are not. We got some thing from the pulp industry, but there is no problem. There are different techniques. We have to very much take different precaution while extracting this cellulose and lignin, whatever it may be, and isolate cellulose nanofibers. Yes, it is possible to make isolation of the cellulose nanofiber. I have shown in electrospinning technique there are different type of collectors. Okay, if the collector is very thin rib, okay, so we will get aligned nanofiber, and you can run for few minutes seconds. Okay, so we will get particular nanofiber on the collector, so we will get isolated nanofiber because diameter is again in the range of 100 1000 up to 1000 nanometers, so we can able to isolate and we can observe also easily.
Okay, thank you so much, sir. So there are no more questions.
Is there any other question?
I think there is one more question.
Yes.
If there is question, you can read. I am
Yes.
unable to.
Yes. Kirti, 1 minute. So, thank you, sir, for a wonderful presentation. I am just curious, what is your source material in extracting the cellulose nanofiber? Did you experience agglomeration on your nanomaterial as you isolate cellulose nanofibers?
Ma'am,
Yeah, we
I have
can.
already asked that.
That already I have talked about this. If there is further any question,
Any question from the panelist side?
Thank you, Dr. Sir. It was a very informative and comprehensive presentation. So I have a quick question. Like, as we use electrospinning, I know it is a very versatile technique, but can you put some light on some of the challenges and what kind of, I remember you said high mass polymers are needed. So can we electrospin any kind of polymers which are having high molecular weight, or is there a restriction?
No, no. There are some restriction. If that polymer is not conductive, okay, we require when we are applying the electric field, okay, that polymer molecules, okay, that may be charged, and if we can charge, then only they are coming align in the your needle, okay. When electric field is applied, then after surpassing the electric field, okay, then they are coming out from the your needle end, and they are collected on the collector. If the polymer is not conducting, okay, then we will only get the sprinkling, okay. It is not continuous nanofibers. There are different properties, the surface tension, conductivity, dispersion of polymer in the solvent. These are all have parameter are affecting on the synthesis of nanofibers.
So it's good for like making
Uh,
nanofibers or
yeah,
conductive
we
polymers.
cannot make all type of polymer into the conversion into the nanofibers.
And you also showed different types of collectors. So
Yeah.
the shape is dependent on, the shape of the collector, it gives varying sizes or of these nanofibers.
No, collector is not giving size. Size will be controlled by your polymer concentration, your collector to tip distance, syringe of the tip and collector
Right.
distance. How much, if there is longer distance travel by your polymer, then automatically your fibers are getting thinner, lower diameter. Okay, and collector does not play influence role on means type of fiber diameter. Fiber diameter play controlled by polymer concentration, your electric field, and tip to collector distance.
And like I know that most of the time when we try spraying, I'm sure clogging must be a very common thing that must be faced as challenge.
Yeah. So we have to monitor every time, and there may be clogging, so we have to discharge. Okay, there is always one discharge stick is there, so we have to discharge and remove the clogging from the tip of the syringe.
So can we call this method as a high throughput method, or is it only for R&D scale?
Already there are commercialization is already there. People are making 1 meter by 1 meter type big seats.
I see.
We are also making 1 feet by 1 feet seat in the lab.
And how long it takes?
It takes a lot of time because again that fibers are nano,
Right.
and when
So
we
say,
are
for example, like a 1 feet by 1 feet and a thickness of say
it will yeah
few
it will
5 millimeter.
it will take 8 to 10 hours.
And approximately thickness will be in millimeters,
It is not millimeter, it is micron, 20
microns,
micron to 50 micron, not millimeter. If you
not
want to
even a
go,
millimeter. Okay.
yeah, not.
Okay. Okay. Thank you so much, sir. It was very
Okay.
informative talk.
Okay. Thank you, everyone.
Thank you, Sanjay sir, for an interesting and innovative lecture on thermoelectronic and biopolymer material for supercapacitor application. As the conventional method of pollutant removal are tedious process and require the optimization at chemical method, you beautifully explained the role of this material in this area. Thank you once again for memorable lecture, sir. Thank you. Kirti, can you please invite our next speaker, Professor Rohit Srivastava, sir? Kirti,
Yes,
over to
ma'am.
you. Yes.
Now I would like to introduce our third speaker, Dr. Rohit Srivastava from Dayalbagh Educational Institute, Agra. Dr. Rohit Srivastava, Professor and Head Department of Chemistry at Dayalbagh Educational Institute. He has experience of more than 36 years of teaching to undergraduate and postgraduate classes. He is an active researcher in the domain of chemical science for more than 39 years and supervised successfully 12 PhD and 7 MPhil students. His current research interests are in the areas of solar hydrogen generation by photoelectrochemical and photocatalytical splitting of water. With total citation of 3,700 and H index 34, He has published 122 papers in peer-reviewed journals. He has successfully completed several research projects funded by different government agencies, including 2 Indo-US collaborative research projects, one funded jointly by DST India and NSF USA under Materials World Network Program of DST, and the other by UGC under 21st Century Knowledge Initiative Scheme. Today, title of his talk is Future Energy Options and Solar Hydrogen, Challenges and Prospects in the Indian Context. I welcome you, sir. I request you to complete your talk in 45 minutes, followed by 15 minutes question answer session. The platform is all yours, sir.
Okay, very good morning. I hope you are able to see the presentation. Please confirm.
Yes, sir.
Okay. Thank you. Very good morning to all the participants in this workshop. I'll try to follow the timeline that has been given to me. This presentation is on future energy options and solar hydrogen, challenges and prospects in the Indian context. This presentation is divided into 4 segments. I'll begin with current energy scenario in the country. Then I'll give you just a comparison of renewable versus conventional sources of energy. And I will introduce the solar hydrogen as a candidate. And then I will briefly share with you the R&D efforts that we have taken in last few years on hydrogen generation. Now, as you all know, the country's inclusive growth hinges critically upon the availability and accessibility of energy to all, and that too at affordable price. In India, if you see, the primary energy consumption is still dominated by the coal, which constitutes about 52%, followed by oil, 30%. And the renewable energy component is very small at present. Now, India's per capita energy consumption is lowest. That's also a fact. And in fact, the wealth of a country is judged on the basis of the energy consumption per capita. So India is not very high on that index. The dominance is of rural population, largely because of that. The consumption of energy is very low. And this rural population depends on commercial sources to meet energy needs. They don't require the conventional sources. India is endowed with abundant primary energy sources, fossil fuels, renewables, unconventional, particularly the wood and biomass. Now, India is committed towards increasing the share of renewable power in the electricity mix. That is something which the government is advocating, that ultimately we have to increase our dependence on renewable energy. And I just want to mention, the government of India is targeting to be a 5 trillion economy by the year 2025. And to support this growth, the energy supply also has to grow at 6.5% per year. By 2030, the total energy requirement for the country is expected to be around 400,000 megawatts. Now, besides relying upon import, this burgeoning energy demand can be fulfilled only by expanding domestic production in petroleum, natural gas, and coal subsectors, and also by giving greater impetus to renewable energy uses, especially in rural and semi-urban areas. Ideally, the renewable energy component consisting of hydro, wind, solar, and nuclear should meet nearly 50% of the total energy demand of the country. Now, I'll just spend a little time on these different candidates on which we have to think. The one is, of course, the nuclear energy. India's present time nuclear power capacity is 6780 megawatt with 22 operational nuclear power reactors. It is expected to reach the level of 22,480 megawatt by the year 2031. Since India is outside the nuclear non-proliferation treaty, developments in the civil nuclear energy sectors are hampered. Good part is that India has thorium reserves and is developing nuclear fuel cycle to exploit it. We have already developed expertise and indigenous technologies on fast reactors also. But still there are a lot of doubts and hesitations about the use of nuclear energy, and these are mainly associated with the safety concerns. This gives you just an idea where most of our nuclear reactors are located. You can see that except Narora, which is probably in the northern belt, and maybe one reactor in the Rajasthan, but all other reactors are alongside the coasts. And major part of the land in the country is not covered under these nuclear reactors. Now, wind energy is another option. It has a lot of potential in India, and we are utilizing very less potential at present. A recent study conducted in the state of Tamil Nadu indicated that just on wasteland alone, over 35,000 megawatt of wind power generation can be established, while we are at present utilizing only 6,000 megawatt. Wind energy is also commercially viable and can support the central government's target on the use of renewable energy. But again, the limitation is that it is not available all through the country. It is available only in certain pockets. You can see much of the dominance is by the states of Tamil Nadu, Maharashtra, Gujarat, to some extent Karnataka and Rajasthan. But the most populated states like Madhya Pradesh, Andhra Pradesh, and even Uttar Pradesh, they hardly have this potential available. Then solar water splitting is also one option in this reference, and a huge potential exists for solar energy harnessing in the country. The idea here is to utilize the solar energy, store it in the form of hydrogen via photo splitting of water. And once hydrogen is generated, this hydrogen can be used as a chemical fuel. Now, to face challenges and gain prospects in the energy sector, we need to foster technological improvements in the conventional energy usages, and also to innovate with rigorous R&D efforts in emerging renewable energy technologies, particularly the solar hydrogen. Hydrogen, I will advocate as a fuel for future. It is a zero carbon fuel. It has the potential to meet the need of a clean, reliable, and sustainable energy carrier, which will satisfy the need of both the earth and the wheel. It is most abundant element on earth. High energy per unit mass is there, which is higher than even gasoline and natural gas. It can be stored in liquid, compressed gas, and hydride forms. We all know that there are certain issues associated with the storage of hydrogen, but it is technologically possible to store it. It can be blended up to 20% with CNG. You don't require major technological changes in our vehicles. With the CNG, 20% blending is possible. It is already being practiced at some places. Possible to use in IC engines and fuel cells, and it can be used as energy for continuous supply. Still, there are few limitations. Very low volumetric energy density and the safety aspects are still a point of concern. Now, Government of India has unveiled in February 2022 a new green hydrogen policy, and a first part of that has been launched, which promises cheaper renewable power, fee waiver for interstate power transmission for 25 years for projects commissioned before June 2025, land in renewable energy parks, and mega manufacturing zones to help local industries wean themselves off fossil fuels. Renewable hydrogen is thus the call of future, and the future, I would say, is not too far. Many people believe that it has already been arrived. Now, when I am advocating the hydrogen as a fuel, actually it's a whole system. It will begin with hydrogen production, then hydrogen storage and transport, then its applications. And in this application, fuel cell technology comes as a big area. Awareness and capacity building is another aspect, and safety codes and standards also need to be developed. But this is a transition which the country and the whole world is hoping to come as early as possible. Now, with this background, I just want to introduce the audience. I don't know, I've been told that many of you are students, research scholars and students. So I'll just spend a time on photoelectrochemical splitting of water. After all, what this process is. Actually, this is a simple electrolysis of water. The only difference is that unlike the two non-photoactive electrodes, in a photoelectrochemical water splitting systems, one of the electrode would be made up of a semiconductor. And that is the most critical component, because that semiconductor electrode would absorb the light, particularly the solar light, when it falls on it. So it should have a strong optical absorption. And once the light is absorbed by the semiconductor, the electron hole pairs will be generated. And these charge carriers must have high electron mobility and must have long lifetime as well. Then these charge carriers will move through the junction, electrode-electrolyte junction, and they will participate in redox processes, oxidation at anode and reduction at cathode, that leads to the splitting of water. So in this reference, the properly aligned band edges is also something which we are looking for. Additionally, because electrode will be in contact with electrolytes, so stability of electrode in contact with electrolytes is also very essential. And last but not the least, I would say the material has to be low cost, because ultimately we have to upscale this technology and use it for large scale hydrogen generation. Now, these are few of the guidelines which have been suggested by Department of Energy USA, their recommendations, that the conversion efficiency, energy conversion efficiency should be at least 10%. That's a target which they have set. The current density for that must be about 10 to 15 milliampere per centimeter square. Material durability should be more than 2000 hours, and cost of hydrogen should be 100 to 150 rupees per kg. Now that includes the production, transportation, and distribution, all. Now coming to, because I have just told you that semiconductor electrode is the most critical component. So a lot of work is underway in looking for the best candidate. What could be the best semiconductor and what material properties can be introduced in that material to meet all these requirements. Now, this is a list of, this is just a diagram to show you what are the different possible candidates and how they are, their band edges are aligned with redox potentials of hydrogen, hydrogen and oxygen. Now, band positions of various known semiconductors relative to redox level of water at pH 1 has been shown here. These do differ with the variations in the electrolyte pH a little bit. So that is also to be taken into account. Now, coming to the main theme of this workshop, you see nano-structured and nano-crystalline materials hold a very important place in this research. Reason being because they have unique optical and electrical properties. They offer high specific surface volume ratio, modified band gap and band edge positions, easy transport of charges, and less defects. So with all these beneficial properties associated with nano-structured and nano-crystalline materials, they become a very strong candidate in this research. And bulk of the research that is being pursued nowadays is in the creation of nano-structured, nano-crystalline semiconductor materials, which can be used as electrode in this whole process. Now, synthesis route that we follow, that also plays a very important role in modifying the material properties. People are using chemical route as well as the physical route. Chemical route are cheaper and they can be easily upscaled. And that's why ultimately we have to depend upon them largely. Spray pyrolysis, CVD, sol-gel technique, potential static anodization, electrode, these are all low cost methods. Compared to that, if you go for physical route like pulse laser deposition, sputtering, vacuum coating, these are all relatively expensive techniques. So that way I would say chemical route are better placed because they can be easily upscaled. Doping is one possibility. It extends absorption in the visible region. Many a times when we are working on high band gap materials, which do not show their absorption maxima in the visible range where bulk of the solar energy is falling, we need to tailor their band gap by suitable doping. The doping also increases lifetime of photo-generated carriers. It reduces the electrical resistivity, and it also creates some surface states, which oftentimes help in the charge transfer across electrode-electrolyte junction. Now, doping can be metallic or it can be a non-metallic. Both are the possibilities, and people are working on both these possibilities. Now, dye sensitization is another area where people are trying their hand. Again, the idea here is that we are using some high band gap material which doesn't absorb in the visible region, and therefore it is unable to absorb bulk of the solar energy. But that electrode is coated with a suitable dye, and the dye is visible absorbing dye. So that dye absorbs the light, and then it transfers energy in the form of electron hole pairs to the semiconductor, and semiconductor does the separation, and then the whole process begins. So this is also one area. It leads to enhanced solar absorption and also a better photo response. But here the issue is the stability of dye. Most of the time it has been seen that the dyes, they have very limited stability. They often get degrade once they are put in the electrochemical cells. Ion implantation is another area where people are working. Metal ions can be injected in semiconductor so that they get implanted in the lattice. And this process modifies electronic structure and may shift photo response to the visible region, particularly when you are dealing with high band gap materials. It may also lead to more effective second generation materials for solar energy utilization. In this reference, swift heavy ion irradiation is another aspect on which we have done some pioneering work. It leads to creation of amorphous band in the lattice, development of sub-nanoparticles on account of grain fragmentation, impurity segregation on grain boundaries, and confinement of impurities in smaller grains. And all these changes hopefully may alter the photo response of the material in PEC cell. With that hope, actually, people are working on this particular aspect. Now, carbon nanotubes is another area which have been put into use into this process. Carbon nanotubes are thin, hollow cylinders formed of graphene, represented by honeycomb lattice of carbon atoms. They offer large surface area and are inert with one-dimensional structures. And it is a report that carbon nanotubes in TiO2 film are known to significantly decrease the charge transfer resistance, and it increases the anodic photocurrent response. Graphene is another kind of materials which have been put into use. It is composed of sp2 bonded carbon atoms, and this is one report which suggests that bismuth vanadate, when it is incorporated with reduced graphene oxide, the whole composite showed remarkable, almost 10-fold enhancement in photoelectrochemical water splitting reaction. So that is also one area where people are trying their hand. Now, this background, I'm coming to the DI initiatives and the progress that we have made in last few years. We have been working basically towards the identification and synthesis of semiconductor material systems for hydrogen generation via PEC water splitting. And our research is yielding a better understanding on following: the most efficient semiconductor, the appropriate and scalable material synthesis protocols, and suitable material modification strategies for significant gain in efficiency. The aim is ultimately to pave the way for upscaling and pilot scale hydrogen generation in future. Right now, we are working on laboratory modules, but that's the ultimate aim on which we are working. Now, this is a chronicle of research progress in our department and the government support that we have been able to garner. We started working in this area in as long as in 2000, almost 2000. So it's almost 22-year-old project on which we are working. We have secured grants from different agencies in the form of projects, funded projects. We have also completed 2 Indo-US projects, one funded by DST and NSF under Materials World Network Program, and another by UGC in collaboration with Arizona State University, which was under 21st Century Knowledge Initiative scheme of UGC. Now, this has already been told about my introduction. We have publications, something around 85 in this particular area. Some 2,700 citations, 26 PhD dissertations have been completed in this area. We have completed projects worth 625 lakhs, and the ongoing projects are 60 lakhs. H-index of our group is 24 to 32. Now, these are the different materials on which we have been working. Few of them are large band gap materials. You can see zinc oxide, titanium dioxide, strontium titanate, barium titanate, and few of them are moderate to small band gap. The problem is that if you are using a large band gap material, they are largely absorbing in the UV region. So they don't absorb the solar light to that extent, but they are stable and they support the photoelectrochemical water splitting very spontaneously. On the other hand, if you use a moderate to small band gap semiconductors, they absorb the visible light, they absorb the solar light, but they do not spontaneously support the photoelectrochemical water splitting, because oftentimes their band edges are placed in a manner that it doesn't support the charge transfer across electrode-electrolyte junction. Now, major challenges are that we are looking for a band gap energy around 2 electron volt, straddling band positions with redox potential of water, strong optical absorption, stability in electrolytes, and the cost effectiveness of the material. That is also very important. Now, these are few of the modifications that we have tried in the past, and I've just mentioned some of the results here, highest photo response that we could record. With iron oxide, we tried doping, we tried swift heavy ion irradiation, doping, titanium, zirconium, swift heavy ion irradiation, 120 MeV silver ions and silicon ions. We have also tried the quantum dot sensitization, cadmium selenium, and these are some of the values that we could record: 3 milliampere per centimeter square and 2 milliampere per centimeter square with titanium doping. Similarly, with zinc oxide also we have tried doping, swift heavy ion irradiation, surface embedding of metal nanoparticles, and even the co-doping. Titanium dioxide, we have attempted doping with cadmium and iron, and SHI irradiation with 120 MeV silver ions. Strontium titanate, barium titanate, again doping and SHI irradiation. And similarly with cupric oxide and cuprous oxide, again doping with silver and iron, and SHI irradiation with gold ions. Now, these are the different aspects on which we are working. We are working on bilayered systems nowadays, because these are the advanced systems. Much of the work that is coming, being published nowadays in this particular area, or on bilayered systems, where we are trying to combine the advantages of low and high band gap materials together to generate a composite system which will yield a better results. So bilayered systems, we have studied various of them. Then we are also working on the role of plasmons, particularly gold and silver. We are working on conducting polymers, We have not done much work, but this is an area where we are planning to work. And influence of morphology and electrode-electrolyte interface, graphene, MWCNT, and their role in enhancing the photoelectrochemical response is also something on which we have done some work. We are also working on theoretical aspect of this whole research, particularly using density functional theory. And Dr. Sumant, who is there in your MIT University, he is the one who actually worked in this area in early years. One or two students have also worked on bio-inspired systems. Now, because there is a paucity of time, I can't cover all these systems. So I'll just share with you a glimpse of work that we have done on zinc oxide. That is one material. It's basically a large band gap material. You all know, high band gap material. Its band gap is around 3.2 electron volt. But the advantages with zinc oxide is that it's had long lifetime of charge carriers, high electron mobility, strong optical absorption, and the straddling water redox potentials. And it has a very rich defect chemistry, which also plays a very important role in making it as a good candidate. Now, we have done some work on this. The first part is that electrodeposition. We prepared actually zinc oxide by electrodeposition and sol gel. Electrodeposition and sol gel. And these are the XRD results. A comparison of these are the results for sol gel synthesized films, and these are for electrodeposition synthesized films. And the polycrystalline nature was confirmed with dominant presence of hexagonal woodside zinc oxide. Average crystallite size was 32, 33, 39 nanometer for sol-gel derived films and 42 to 49 nanometers for electrodeposition derived films. These are the optical absorption curves, and you can see that the material is largely absorbing in the UV region only. ED derived films with 2 and 1% nitrogen incorporation yielded highest absorption, and the decreased absorption with SG derived films is attributed to the improved crystallinity. A moderate marginal drop in band gap occurred on nitrogen incorporation. These are AFM images. There was preferred C-axis oriented vertical growth of nanocrystallites. Dominant evolution of woodsite zinc oxide is there. And compared to SG derived films, the ED derived samples are rougher, suggesting relatively fluffy evolution of nanocrystallites. These are SEM images. We observed homogeneous morphology, and ED derived films indicated agglomeration that increased with the rise in nitrogen concentration. These are the PEC IV plots where you can see that compared to the dark line, the current that we observed under darkness, the black line, the current that was recorded for different samples under illumination was relatively high. And this difference, the significant difference in the current density is an indicative of the photoactive nature of the films. The SG derived films yielded higher photocurrent and recorded highest gain, almost 100% compared to pristine samples. At higher nitrogen concentrations, the photocurrent decreased in both set of samples. This is another part that we have done with zinc oxide. We actually embedded the zinc oxide films by silver and gold nanoparticles, which we could synthesize by biological reduction using an algae, Spirulina platensis. The zinc oxide film surfaces embedded with biologically derived nanoparticles were grown by sol-gel. And this is an XRD pattern of the nanoparticles, the metal nanoparticles. And it confirmed the existence of metallic silver and metallic gold, and average crystallite size increased with the increase in precursor solution. And now these are the XRD patterns of the films. And once again, the peaks, the dominant peaks confirmed the evolution of woodsite zinc oxide with average crystallite size 35 to 50 nanometers. Compared to pristine samples in silver zinc oxide and gold zinc oxide films, the crystallite size decreased, while dislocation density and microstrain values increased. Actually, it is all because of the strain in the lattice that the crystallite size was found to be decreased. These are the SEM images, and here we could observe some nano-ridge structures which are clearly evident in AG zinc oxide films. But these structures were not there in gold nanoparticle embedded films. So this was a comparison between silver and gold nanoparticle embedded films, and particle size distribution estimated from JMH software matched with results that we could obtain from Scherer's computation using XRD data. These are AFM images. Once again, nano-ridge formation can be seen, peaks as high as 200 nanometer and valley to valley separation of 600 nanometer was observed. The root mean square surface roughness increased compared to pristine samples, and silver zinc oxide films are relatively rougher. These are optical absorption plots, and absorption pattern being nearly same in all the samples suggest that samples are uniform on crystallinity and stoichiometry. Band gap energy ranged 3.1 to 3.2 electron volt is still on a higher side because basically the base material is zinc oxide. Sharp absorption peak at around 400 nanometer is a typical feature of hexagonal woodsite phase of zinc oxide. And now these are the EDX patterns, and it confirmed the elemental composition of zinc oxide films because we could see the signals of zinc and oxygen being present in the same ratio as they were expected. And the existence of silver and gold nanoparticles were also detected. These are the photoelectrochemical IV plots, and the maximum gain in photocurrent to the tune of 150% respectively were observed with Ag zinc oxide and gold zinc oxide films. And electronic properties of films optimized by suitable microstructure appear critical in PEC performance of these films. And now this is another feature, another aspect that we have investigated. Actually, surface properties, we could see from literature that surface properties of semiconductor photoelectrode, particularly the surface area, topography, surface defects, and nanoformations, they play a crucial role in PEC splitting of water. Therefore, we attempted chemical etching by acids. The zinc oxide films were subjected to chemical etching. And this could be a very low cost method to alter the surface characteristics and raise the effective surface area. The chemical nature and the concentration of etching reagent here play a very important role. Particularly the etching duration also becomes a very critical. But you have to control this etching. Otherwise, the whole film may dissolve. So effect of controlled surface etching of zinc oxide using 5 different acids. We used organic acid, acetic acid, formic, succinic, tartaric, and orthophosphoric acids in the concentration range 10 to the power minus 4 molar. And the contact duration was varied from 20 seconds to 120 seconds. The controlled surface etching here led to significant fall in average thickness and density of films, indicating partial dissolution due to lateral and longitudinal penetration of etching ions, hydrogen ions in the host lattice, evolution of a more porous structure, and a fall in the in situ electrical resistivity, and the creation of more oxygen vacancies in the lattice, which decreased the resistivity. These are the XRD patterns for the films, and it indicates that there is some tensile strain in the lattice, probably due to some reorientation of the nanocrystallites, which might have occurred on account of etching. The SEM analysis again confirmed nanoridges with peaks and valleys at the surface. The effect is due to slow evaporation of solvent. Actually, while analyzing why these valleys were formed or nanoridges were formed, we could come to this conclusion that the effect is due to slow evaporation of solvent and the sufficient time available for the gel particles to relax structurally and pile up to undulated nanoridge structures. That could be an answer. So this is what we have proposed in this study. And the unique structure is known to provide effective hole blocking layers, besides increase the interfacial area for electron collection. These are AFM plots. The RMS surface roughness increased after etching. The decrease at higher durations is indicative of the complete peeling off of the top layer, as it led to significant fall in film thickness as well. These are optical absorption plots, and the absorption peak at around 400 nanometer is a characteristics of zinc oxide woodside phase, and there isn't much change in the band gap. Electrochemical measurements and computations based on the use of Randall-Sevick equation yielded effective surface area of films before and after etching, and we could see that there is a significant gain in the effective surface area after etching. The PEC measurement data is shown here. The PEC photocurrent increases to a maximum and drops again in higher duration etched films. Maximum increment was recorded with films which were etched with succinic acid and formic acid. So that means the role of the organic acid and its structure is also very critical to make it optimal. Otherwise, excessive etching or too less etching, it doesn't serve the purpose. It has to be etched optimally to get some benefit. Now, this is another area I just mentioned, that we are working on bilayered thin films and also the coarse shell nanoheterostructures. Here, the idea is to combine a small and large bandgap materials deposited one over the other, and so that they may absorb full solar spectrum more efficiently. And if the energy bandages match at the junction of the two materials, a better and efficient separation of photo-generated electron hole would be possible. So with that idea, we have done some work on these bilayered films. Now here, these are the XRD pattern. Basically, this is a bilayered films of zinc oxide and WO3. These are the AFM images. Here you can see the XRD patterns and the optical absorption pattern. The films showed moderate absorption in the visible region with partial redshift, and XRD analysis confirmed the polycrystalline nature of the samples with no secondary phase evolved. I-tube was used as a substrate to grow these films. So we could see the signals corresponding to I-tube, zinc oxide, and WO3 in the XRD pattern. These are the SEM images, and side by side you can see the index patterns. Both interfaces, zinc oxide and WO3, are clearly visualized. WO3 exhibited porous morphology, while zinc oxide possesses homogeneous morphology with small particles. And index of bilayered films indicated zinc, W, and oxygen elements in the expected atomic percentages. These are the photocurrent plots, IV plots, and we could see an improvement, a significant improvement in the current in bilayered samples, which was largely due to enhanced absorption of incident light, which correlated with the increase in film thickness at lower range of thickness variations. Now, this is another bilayered samples which we have done, barium titanate and zinc oxide bilayered films, and just a glimpse of various observations that we could record. XRD pattern, this is optical absorption pattern, and here you can see the photocurrent. This is a photocurrent curve, this is optical absorption patterns. Now, improved photocurrent in bilayered samples here was again ascribed to increase in thickness and effective separation of charge carriers at the interface. Now, as far as core shell nanostructures are concerned, we have done some work on copper oxide, titanium dioxide core shell nanostructure. And here, the titanium dioxide shell was also doped with silver. So it was a copper oxide core, and it was coated with a titanium dioxide shell. The titanium dioxide was also doped with silver. Such systems actually allow alteration in particle morphology, compositions, and surface properties, and all of these will play significant influence on PEC water, photocatalytic water splitting. Actually, this work is not on PEC water splitting. We could generate the powder of this core shell nanostructure, and that powdered sample was used as a photocatalyst to study the photocatalytic water splitting. Here you can see some of the results, XRD patterns, you can see on the right hand side, and these are the SEM images of the samples, which showed absorption in the visible region and redshift in the band gap energy. Here you can see the optical absorption. SEM analysis of prepared samples indicated porous nanostructures. Now, this is the hydrogen production as it was observed on a time scale, both under artificial illumination and as well as in the solar illumination. That means in field conditions. In the artificial illumination, you can see on the left-hand side, the hydrogen production, how it has been increased. But in the solar illumination, when we moved to natural illumination, there, of course, the hydrogen production was not of that high order, but still you can see that the material is photosensitive. Photocatalytic splitting of water, largely it is occurring in the UV light, and that's why in the sunlight, the response is not of that order. And these are some of the results which we could see. Solar to hydrogen conversion efficiency, the hydrogen yield that we could record in micromoles per hour per gram in UV light and in sunlight, and the quantum efficiency that we could calculate. Now, coming to the future directions, I would say mixed oxide systems, ternary, quaternary, or even higher, they hold a lot of promise. Here, I would say that there are 40 plus elements which are important, and their composition, if we look into, it would generate something around 2 million possible combinations. So if anybody works on 20 combinations per day, even then it will take 273 days for us to screen out all the possibilities. And that is why people are trying to go for fast screening procedures. And in this reference, I would say the theoretical computations play a very vital role. We can, without doing any experiment, we can quickly go for theoretical computations to screen the suitability of a material. And if it is really promising on theoretical calculations, then someone can go for experimental observations on those. So this is one area. Then besides, right now we are working on oxides, and we have been working in all these years primarily on oxides. And the reasons are very obvious. Oxides are very stable, they are low cost. and they can be easily generated, easily synthesized. But the other class of semiconductors are also there in the list: phosphides and selenides, graphene and CNT based systems. They can definitely be tried, and layered structures, on which we have already started working, is also a possibility. Now, this research has been funded very liberally by the government agencies like DST, Department of Atomic Energy, VRNS, University Grants Commission, AICT, and MNRE also. We have just completed one MNRE project also, under which we have been able to procure an FESEM unit in our department, which is now operational. Now, we had collaboration with Arizona State University, University of Maryland, Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, Indian Institute of Technology, Kanpur, IIT Delhi, Bhabha Atomic Research Center, and Inter-University Accelerator Center, New Delhi. We had good collaboration with the scientists from all these organizations, and we are still working in collaboration with them. I hope I have justified my presentation in 45 minutes. I conclude at this point. Thank you for your kind attention. If you have any query, I will be happy to answer. Thank you.
Thank you so much, sir, for wonderful talk. There are few questions.
I think
First question from Warren.
Kirti, can you ask Dr. Sumant Upadhyay to
Can you be a little louder, because I'm not able to?
Okay, sir.
Yeah.
First question from Warren Rosario.
Ji.
Thanks
Kirti,
for
can you
such
please
a detailed
ask Kirti, can you please ask Dr. Sumant Upadhyay to first talk? Just comment on this talk.
Thank you, madam. Sir, thank you so very much for your time. I hope am I audible?
Yes, yes.
Yeah. So thank you so very much for your time and your valuable talk on, especially on photoelectrochemical and photocatalytic water splitting. It was indeed a great pleasure to hear from you after a so long time. And thank you so very much. So Kirti, now you can ask questions from the audience if you have any.
Okay, thank you, sir. Sir, the first question is from Warren. Thanks for such a detailed presentation. I have a few questions. Which do you think will be the more dominant form of energy in India in the future, nuclear or solar?
You see, nuclear is again a very good candidate, I would say. Nuclear has a lot of potential, and solar also has a very, very promising source. But the problem with the nuclear energy is that people are a little susceptible about the nuclear energy. It has a lot of safety issues, and there are technological issues also. So that's a problem. Compared to that, solar energy is something which can be very easily adopted, and it can be put into use in small sectors as well. That means from big cities to small villages, small towns, it can go anywhere. You just generate, you have to generate the system, and then solar energy is available everywhere. So people can tap solar energy wherever they are in the need of energy. Whereas if you generate nuclear energy, nuclear electricity, again, you will be required to transmit that electricity to different places where the consumers are. So suppose somebody is living in a very hilly terrain, you can't have a nuclear reactor there, but the energy needs will be there because people are living there. So I think the solar energy would definitely be a good candidate there. But the ideal situation would be that we have to make a compromise between both the. You cannot depend upon only one source of energy. You have to look into renewable energy as a big bracket, which has a nuclear energy, wind energy, solar energy, and any other hydro energy if it is there. So you have to look into the availability of all these energy forms, where they are, and how easily we can tap to them.
Okay, sir. Can you name some promising hydrogen generation and storage technologies?
You see, hydrogen generation technology, if you ask for from conventional fossil fuels, that technology is already there. You see, hydrogen is not just a fuel, it's a material which is being used in the industry for different purposes. For example, in the urea production, hydrogen is being used as a raw material. So they depend upon the hydrogen that they get from fossil fuels. The idea here is that we should stop our dependence on fossil fuels. They are being depleted at a very fast rate and they are creating a lot of pollution problems. So we have to depend upon those sources of hydrogen which are renewable and clean. And in that reference, I would say solar water splitting can be a good option. But the solar water splitting is again, it can be done by photocatalytic method, or it can be done by photoelectrochemical method, or it can be done by photovoltaic coupled with electrolysis. So there are different technological options available. Photoelectrochemical method is superior to that extent, that because it does the absorption of light and the water splitting in one go. So here the efficiency is expected to be high, but it has its own challenges, which I have already mentioned in my talk. So, I mean, the race is still there. Nobody is a winner at this scale. No technology is a winner. People are still struggling to find the best answer for renewable hydrogen generation.
Again, he asked, how long do you think it will take to transition to hydrogen transport and distribution infrastructure?
You see, the solar water splitting by photoelectrochemical water splitting, the first report came in 1972. People may say that almost 4 to 5 decades have passed, and this technology is still struggling to be evolved. But I would say in the history of science, 50 years is not a very big time. It's a very small time. These five decades of research has led us to some very interesting conclusions. Now we are better placed. We can understand the whole process in a better way, and we can see what and how it can be optimized. So we have to wait. I cannot give you a very precise timeline for that in next 20 years or next 30 years or next 10 years, the results would come. The technology is evolving. We have to be a little patient. And second thing is that we have no choice. Fossil fuels are being depleted. That's a fact. They are going to be finished sooner or later, maybe another 50 years, another 100 years. They are going to be finished. There is no doubt about that. So we have to depend upon these non-renewable sources, and solar energy is a very promising candidate. And when you are typing solar energy, then its conversion into chemical fuels like hydrogen becomes a very promising prospect. So we have no choice. We have to work on this.
Okay, sir. Next question is from Shringika Soni. Thank you, sir, for this wonderful talk. What do you think of superiority of bio-inspired nanomaterials in solar energy compared to inorganic nanomaterials in terms of energy transfer and electron transport? Do you think bioresource can be more beneficial in renewable energy?
Yeah, sure. It's a very upcoming area of research, I would say. Bio nanomaterials or coupling the inorganic nanostructured materials with biomaterials. It's a very promising area, very promising. A lot of reports are coming up. So we are pretty hopeful that this could be a good approach, particularly if we could absorb solar light efficiently, and we could generate the photoelectron charge carriers, photo-generated electron hole pairs efficiently. So it will serve the purpose. People are working on these bio kind of biosystems. And we have also done some work on bio-inspired systems, cobalt acetate and all that. We were trying to couple these with our inorganic systems, and we could get some good results as well, which we have published. So it's a very open area. A lot of work is coming up.
Okay, sir. Sir, next question is from Chinmay Shukla. Sir, it is known that 1D nanostructures has a better absorption of sunlight with better conduction properties. So is it possible to grow 1D metal oxide structures using swift heavy ions under certain conditions to scale up and decrease the cost while having precision?
That's a possibility. One-dimensional, growing the one-dimensional nanostructures and then going for swift heavy and irradiation is something which you can try. I'm not very clear how it will work. I have no idea, but it can be pursued. It can be a good idea to work on these systems. And definitely one-dimensional nanostructures hold an edge over multi-dimensional nanostructures. So they can be thought of. It can be a good idea to work on these systems.
Okay. He also want to know, sir, how can one ensure an effective junction being made for bilayer materials?
Actually, this junction and its efficacy in photoelectrochemical water splitting depends upon the alignment of the band edges. The crux of the whole research is that the material should be highly absorbing. It should absorb the solar light efficiently. That's one aspect that you have to look into. And the second is that once the electron hole pairs are created in the system, they should not recombine. So that means there should be some mechanism, inbuilt mechanism available in the system, which should separate them as quickly as possible. They are taken at different ends. One goes to the cathode, the other carrier goes to the anode. If that happens quickly, then the electron hole lifetime will increase and the efficiency of the whole process will increase. So the junction characteristics actually should support this electron hole separation. The band edge alignment should be such that once the electron hole pairs are created, they are quickly separated because of the p-n junction formation at the junction. If that happens, that junction will facilitate, it will support the photoelectrochemical water splitting. That's the only criteria that we have to look.
Okay, sir. Sir, next question is from Jaslyn. Hello, sir. Thank you for your very nice presentation. I'm just wondering what software or computer codes to calculate electronic structure and materials modeling in DFT.
Actually, I don't have much idea about this. Dr. Sumant was the pioneering worker in our group. He did the pioneering work in this area, and then it was followed by a few other scholars. So I think Dr. Sumant can give a better answer. They are using basically quantum espresso probably. Dr. Sumant can throw some light on this.
Dr. Sumant, you can.
So you can use any open source software or any paid software for that. So we have used Quantum Espresso, as Sir has said, and we at MIT we have a very good computational resource, and the software is QuantumWise ATK VNL, which is a paid one, which is a paid software. Thank you.
Okay, any other question? I'm still online.
Sir, I have one small query that that most of the researchers now they are focusing, I mean, they are saying green hydrogen, and they are actually using photovoltaic cells, right? They are storing that sunlight energy into in batteries, and they are just passing that energy for that electrolysis to happen, and they are just using polymer electrolyte membranes and just to have the exchange for H positive ion for the hydrogen generation. So my question is, this photoelectrochemical water splitting or that process that they are following, I mean, which one is according to you is better for green hydrogen?
Actually, this switch over from PEC to PV electrolysis is, I would say, it is largely because of the pressure from the government. The pressure from the government wants to quickly show some results that the hydrogen, renewable hydrogen, is being generated at some because of some technology there. You see, here the fact is that photovoltaic cell technology is mature, and the electrochemical electrolysis technology, that is also mature. So people are trying to couple the two. the photovoltaic cells they use to create electricity, generate electricity, and then that electricity is fed to the electrolyzers to split water and generate hydrogen. But here the problem is that it's a two-step conversion. And in any two-step conversion, if you say the conversion efficiency of the first process is say 20%, the other process is also 20%. So the overall efficiency will be 20% of 20%. So the efficiency is going to be very low. Compared to that, if you see the photoelectrochemical water splitting, here the conversion is going to be in one step. So it is expected that the efficiency would be high. But I would again say that photoelectrochemical cell technology is not that matured as is the photovoltaic cell technology or the electrolysis technology. So it's not a comparison. I would say you have to wait for photoelectrochemical cell technology also to mature, and then only it can show itself as a better candidate compared to the PV electrolysis modules. Secondly, in the PV electrolysis module, we are forgetting the cost of batteries. If you are storing the electricity in batteries, these batteries also have a lifetime. After some years, maybe 2, 3, 4, 5 years, these batteries become non-operational and you have to replace them. So the replacement cost of these batteries, and then what will you do with these old batteries? That means their, you can say their disposal, that would also be an environmental issue, environmental problem. So these are the comparisons. I will not say which technology is better, which technology has won the race. The race is still on, and people are working on different options. What will be the scenario after 40 years, after 50 years, that is still blurred. One has to work on different options, different possibilities, because we don't know what is going to help us in the long run.
Thank you so very much, sir. Thank you.
Okay, thank you. Thank you.
Thank you, sir.
Professor Srivastav, I just wanted to compliment you for your excellent talk. I see loads of complimentary messages for your talks in the chat box. So people are asking your slides as well. They have given their email IDs. So, I mean, I thank Dr. Sumant Upadhyay also to have invited you here. I think we must hear from you again in probably in physical mode. I know the topic that you've taken up today is truly towards reaching the sustainability goal, but because of lack of time, we are not able to discuss to that extent. So I really thank you from the bottom of my heart for giving such an informative talk and a very good discussion indeed.
Thank you for the organizers and particularly Dr. Suman for giving me this opportunity to have some time with you and discuss few things. Thank you to all of you.
Thank you, sir. Thank you so much. Kirti, can you please invite our next speaker?
Yes, ma'am. I would like to introduce our fourth speaker, Dr. Sampa Saha from IIT Delhi. A polymer scientist, teacher, and consultant, Dr. Sampa Saha is the Associate Professor of Department of Material Science and Engineering at IIT Delhi. An alumnus of Calcutta University, BTech, and IIT Kharagpur, MTech, she received PhD in polymer chemistry from Michigan State University, USA, under the guidance of Professor Gregory L. Baker. After a brief stay at University of Michigan, Ann Arbor as postdoctoral research associate under Professor George Lan, she moved to Singapore to join as a research scientist, BASF Southeast Asia Private Limited. After gaining industrial research experience from BASF and ProChem Singapore, she joined as research fellow at School of Material Science and Engineering, Nanyang Technological University, Singapore. Since 2015, she started working as assistant professor at IIT Delhi. Recently, she became editorial advisory board member of Journal of Macromolecular Science, Part A. Her research area spans from biodegradable polymeric particles to polymer brushes. She emphasizes on multidisciplinary approach to solve problems and hence believe in strong collaborative efforts. Her group works on multi-compartmental biodegradable polymeric particles for drug delivery biodegradable multi-layered polymeric particles for packaging applications, surface modification with polymer brushes, nanofibrillated cellulose for agricultural and biomedical applications, biodegradable genus particles for water remediation. Title of our talk is Anisotropic colloidal surfactants and their applications in water remediations. I welcome you, ma'am. I request you to complete your talk in 45 minutes, followed by 15 minutes question answer sessions. The platform is all yours, ma'am. Hello, ma'am.
Varman, can you please check? She joined or not?
Dr. Saha, can you hear us? She's there in the meeting. Let me give a call to her.
Hello. Hello.
Hello.
Hello, ma'am. Yes, we can hear you.
Yes, ma'am.
Hi, Dr. Dano.
Yes. Good afternoon, ma'am. How are you?
Yeah, I am fine. Somehow recovered from COVID.
We are really glad that Dr. Saha accepted my invitation in spite of being suffering from just recovered from COVID. Thank you so much.
Yeah,
So kindly share your slides.
sure. Okay. My slides are visible.
Yes, ma'am.
Okay. This one. How can I hide this bar? There is one black bar. Not sure how to hide this bar.
IT person, can you help?
Yeah, this one I don't know how to hide this because this is going to.
I'll just take the help of IT person who's in the meeting.
Hide. What is?
Puneet ji, are you in?
Yes, ma'am.
Ma'am is facing some problem. Can you please help?
What kind of problem, ma'am?
So the problem, it's not a problem. There is one black bar is coming. It's covering pretty much a part of my presentation.
You can minimize that.
How can I do that?
You drag it and drop side to ma'am.
No, but it's either it is going up or going down. I cannot do it. It's okay then. Leave it
But
like
we are able to see. I am not getting. I'm not seeing any
bar.
black bar.
Then that's fine. Then nobody
You
can.
can
See.
change first. You can see your slide is changing or not.
Acha. Okay. So why slide is also? Is it changing, right?
Yes, ma'am.
Yes.
Is it? Okay. Okay. Everything is fine now. Okay. Because of my cough now, I have to take water in between very frequently. Sorry for that interruption. Okay. So, good afternoon, everyone. Welcome all to my talk. Today, my topic of my talk would be on anisotropic colloidal surfactants and their application in water remediation. So, before I go into the detail of my talk, so what I this is also another one. Okay, so before I go into the detail of my talk, so I would like to introduce you what in IIT Delhi, what we are working on. So in IIT Delhi, we are working on mainly three different areas. One is two of them based on the particles and particle science and engineering, and then third one is based on the surface modification or surface engineering. So all are correlated or interlinked with each other. So the first one, what we are working on to make multi-layered particles, they can be coarse shell or they can be in side-by-side form, that can be Janus particles, they can be in different kinds of architecture, okay? We can tune the size, shape, and various morphology by using emulsion solvent evaporation technique. So let me use this pointer. Okay. So now this kind of particles, we have already demonstrated their application in various fields like food packaging to prolong their shelf life. Say, for example, when you are talking about multi-layered particles, means the particles will have different layers and different layers can have a different active packaging ingredient. Say, for example, one layer will have antioxidant, another layer will have antibacterial, so that the whatever the food can be stored in that package, which will have these particles in there, and then particles will release antibacterial, antioxidant in their own fashion and a desired fashion, and the food's shelf life can be prolonged. So this was the work what we have already published in several literatures. And then second one is thermal energy storage materials. So based on this similar emulsion technique, we were able to make a porous particles which gave us a very high thermal energy storage ability. And then with that high thermal energy storage ability, we have already demonstrated that these particles can be used for construction, building applications, as well as for refrigerators or AC applications. Okay, and so this is this work also we have published in several papers. The newest one is applied energy, where we have published this work. Next is we are using the electrohydrodynamic coating technique that we'll be discussing today. So this is also a particles, but here we can make a different shape and different size and different compartment based on this particular technique that's called electrohydrodynamic coating technique. So in this technique, what we have, it's just a simple simple electrospinning only, but you can have a, instead of one needle, you can have a multiple needles, and you just have to put the multiple needles jot together, framed in side by side fashion, and then you can pass through the different polymers through the different needles, and then you can get a multi-compartmental particles. Means different needles will have different polymeric solution. So after evaporation of the solvent, you can have a different a single particles, but having, let's say, three different compartments, having three different polymers in those compartments. So each polymer, each compartment consisting of these polymers can have a different functionalization, different properties, and they can release the drugs for drug delivery applications. So they can release multiple drugs and solve polypharmacy problems. And then here we have also used this technology to use to alleviate the groundwater remediation problem. Also for food packaging, this bicompartmental, tricompartmental particles can be used, as I mentioned before. But the advantage of this technique is over the emulsion would be you don't need to involve any solvent. I mean, the minimal solvent will be used just for the jetting, but no need to purify them and then get the solvent out. Many more extra steps will be removed, and on top of that, encapsulation efficiency of the drug will be highly improved. So whatever the drug or actives will be encapsulated, it will be 100% encapsulated over there. There is no loss like emulsion. So it has a pretty good advantages, but disadvantages is it cannot be applied for any polymers. Okay, so in that case, emulsion is pretty much you can apply for any polymers, but this techniques has its own disadvantages. Let's say you want to make a tricompartmental or bicompartmental polymers, but one is completely hydrophobic, another is completely hydrophilic. It will be very difficult for you to get a particles made of completely two different kinds. Okay, a bulk compartments made of one hydrophobic, one hydrophilic is difficult. So they will not make a interface stable, and they will just break apart. So these are the pros and cons of this technique. So so after that, what we are working on is polymer brushes. So polymer brushes means a assemble of polymeric chains at a third to the surface by its one end. Okay, so it's like your toothbrush, where in your toothbrush the bristles of the toothbrushes are tethered to the substrate just by one end. It is just the same. Okay, so here different kinds of substrate, whether a polymeric substrate or inorganic substrate, we have demonstrated to grow polymeric brushes using controlled radical polymerization technique, and we are able to generate different kinds of pattern surface, different kinds of architecture of brushes, and then they were able to show anti-infective properties, highly effective for implant biomaterials, because implant biomaterials, they always suffer from infection assisted problems. So that complete infection resistant materials we can make just by changing a thin layer of polymer brush onto the surface of the implant. Okay, and then there are many other areas like a biosensor, biopatterning, everything you can do using this polymer brush, putting a polymer brush in precise manner onto the surface. So these are the works pretty much what we are currently working on in our lab, and these are our few publications which came into the recent years. Now moving on to today's topic, that is anisotropic particles. So what is anisotropic particles? So particles which are not isotropic in every direction. Isotropic particles means what? They are same at every, their properties remain same at every direction. So let's say if it's a spherical particles, completely spheres and made of a one single polymer, then you can say, or even if it is made of a mixture of polymer but they uniformly dispersed, so that the every direction properties remain the same. So that's called isotropic particles. But when we are calling anisotropic particle, at least one of the direction, the particles behavior will change. Either properties will change, or its composition will change, your shape will change, either will change in one of the directions, then we call it a anisotropic particles. Okay, so we will be mostly focusing on biocompatible anisotropic particles, because we are the group in IIT Delhi, we work on biodegradable, biocompatible polymeric materials. So we are main focusing on those biocompatible anisotropic particles. There are very different kinds of shape you can make using shape anisotropic particles, which comes under shape anisotropic, or surface anisotropic particles, means only one of the surface of the portion of the surface of the particles will be only modified. Maybe the particles will be isotropic, but one of the part of the particle's surface will be modified. So overall, it is a overall it will be anisotropic particles. Or let's say particles core will be anisotropic. Let's say this is a cup-shaped particles. Core is anisotropic, but you can have a uniform surface coating. Overall, the surface modification will happen. So, but this is also anisotropic particles, because the surface modification might be overall uniformly everywhere, but the shape is anisotropic. So, of course, the directional property will change. Another classification under this anisotropic is compositional anisotropic. Means their shape might be same, spherical only, but at different direction their composition might change. Means one direction you will have one polymer with another inorganic materials, another direction will have another different polymers, no inorganic materials, something like that. So we would like to play around all those particles geometry, particle morphology, particles architecture, by using the tools what we have, that is electrohydrodynamic cojetting technique. Okay, as I just mentioned, using this technique you can have a multiple polymeric solution pass through the needle, and you can make either spheres, rods, discs, any kinds of shape. And then even in it is a spheres, but what you are putting in every compartment decides that whether it will be behaving as a anisotropic or not. Okay, so if you are interested, you can read our papers which we recently published in many of these journals based on this anisotropic particles. So now the question comes is why we are interested in these anisotropic particles. So what grade they are causing, what isotropic particles cannot give you. Okay, so they are for that, if you want to know in detail, we have recently written a review articles published in Essays Applied Biomaterials. You can go through that and have a really clear understanding how they are different from isotropic and how they can be used in different kinds of applications. The effect on the biodistribution, means the anisotropic particles, the way they travel inside the body and different organ of the body they reach, there is a difference from the isotropic particles. Enhanced targeting ability because of their structure, say a targeting group you have put only into the one of the compartment of the spherical particle. So this compartment will have the targeting moiety which will go and target to the, say for example, cancer cells. So if you want to target cancer cell inside the body, only one of the compartment you just hook the targeting moiety, that will directly go and attach to the tumor cells. So what is the advantage? Another compartment you can have the drug which is going to one compartment for targeting, another compartment to release the drug and they at its desired fashion and kill the tumor cells, so that the other part of the body will remain unaffected, no side effect will be caused. Okay, so controlled drug release profile coming from the incorporation of two or more drugs or therapeutics. So let's say if you want to have a polypharmacy system, that means where you have a 2-3 drugs are required to release at a desired fashion. Instead of taking 3-4 tablets, you can have a one particles which will have a different pockets, and you can have those drugs inside, and drug-drug interaction can be minimized because they are separated in different compartments, and then they can be released at their own fashion. And then
So that is that you can only achieve using this compartmentalized anisotropic particles. So they can also affect on the cellular uptake. Of course, it has been proven that if you change the shape from spherical to hemispherical or cup-shaped particles, the cellular uptake in certain region will be at least double or triple. So based on that also, we have already worked and published our work in different areas, different papers. Anyways, I'm not going into detail into that, but these are the actual advantages what you cannot get from spherical particles. Okay. Now, coming to the application areas, there are, as I already mentioned, targeted drug delivery, cellular uptake, controlled drug release, bioimaging means you are having the particles which is not only releasing the drug, but also you can track the particles where they have gone by having some imaging agent inside the particles. Okay. Now we are coming to the today's topic, which is this one, that is water remediation. So far, very few literatures are there where these anisotropic particles have been used for water remediation. So in this work, in this talk, I'll be showing how these anisotropic particles can also be used for water remediation or water treatment, and then it will have a great consequences in near future. So first, before we move on to the anisotropic particles and to show what is the advantage of the anisotropic particles, first what we have done in our lab, we worked on the isotropic particles first. So first, the question what we had in mind, are they not good enough for water remediation? Okay, so how a particles can serve a water remediator? Let's understand that first. So groundwater, basically what are the contamination in the wastewater will have? It comes from the industry, households or other purposes. Mostly you will have a two different categories, actually three different categories of waste. One is organic waste, another is inorganic waste. So out of organic waste, one is water soluble waste, another is water insoluble waste. Okay, so say for example, if you are thinking of to treat all these three different kinds of waste, one is inorganic, that is metals, metallic waste, another is organic, one is dyes, let's say for example water soluble dyes coming from textile industries, or organic solvent like chlorinated solvent, hazardous solvent, so they are coming from the any industry, any chemical industries. Okay, so all these three different kinds of waste, you can actually treat them by using zero valent iron nanoparticle. This is already known that zero valent iron nanoparticles, they can actually zero valent iron nanoparticles, they can actually reduce the chlorinated solvents, they can degrade the water soluble dyes, they can absorb and change the oxidation state of heavy metals. Okay, so they can purify all those, but what is their problems? Their problem is they are unstable in nature. Zero valent iron nanoparticles very good in cleaning the water, but they are unstable. You cannot use them for prolonged period of time. Or specifically for groundwater application, you need to inject the particles into the ground. If while transporting to the ground, and if it gets agglomerated and loses its activity, it's of no use. That's why you need to stabilize those zero valent iron nanoparticles before it gets oxidized and agglomerated and gets wasted. Okay, so in order to do that, there are many ways people have tried. One is you can put them into the polymeric fibrous mat and encapsulate them in the polymer fibrous mat, and then that mat can clean the water. You can use them as a membrane. In the membrane also polymer encapsulated ZVI will be there, and then they can pass the water through the membrane, it can give the clean water, or else in the particulate forms you can mix the ZVI with the polymer, and you can have the ZVI nanoparticle covered in polymer, and then that particles you can use to clean up the water. Okay, so among all those technology, what we decided to move towards this technology because it's very easy for us to make polymer encapsulated ZVI, that is zero valent iron nanoparticles, and then use those particle inject for the groundwater remediation. You can inject them and then they can travel and they can clean up the water. Okay, so now in this study, so the what we wanted to see, can they degrade water? Yeah, so for all those studies, what they have shown, this polymer stabilized iron nanoparticle, they can degrade water soluble contaminants. Okay, but they can also degrade water insoluble contaminant. But how about DNAPL? DNAPL means dense non-aqueous phase liquid, which is present into the groundwater. So that is basically organic soluble, but water insoluble contaminants. How they will be getting remediated in situ? If we want that, then we need to capture those ZVI into some biodegradable, so that when you inject into the ground, nothing, residue will be there to contaminate the ground further. So biodegradable hydrophobic polymer matrix would be useful, because if there is hydrophobic matrix, that will have a better interaction with the non-aqueous phase liquid. So we decided to choose a hydrophobic biodegradable polymer matrix to encapsulate these iron nanoparticles and to use them for groundwater remediation. So let's see the results. So using the same electrohydrodynamic co-jetting technique, what we did, we have made them micro-encapsulated. Polylactic acid was the polymer and ZVI nanoparticles, those are present into the polylactic acid polymer. And then we made this electrojetted particles, and those particles, it was turned out to be the porous particles, and then that particles we have decided to inject into the groundwater and to see how they can remediate the in situ groundwater by releasing the iron nanoparticles which are present inside the polylactic acid matrix. So what is the role of polylactic acid matrix? They are going to protect the ZVI so that they don't get oxidized, they don't get agglomerated. On top of that, they will, when they'll be transporting through the groundwater, so then they will be preserved, and then slowly, as polylactic acid is a biodegradable polymer, so over the time, by degrading, by water ingression, it will slowly release the iron nanoparticle which is present inside the polylactic acid particles, and then slowly release and then remediate the water in there in situ. So that was the idea, and based on that we have made these particles, and you can see that particles were nearly monodispersed, which we obtained from the electrospinning, electrojetting, and these are some characterization which shows that ZVI presence into this polylactic acid matrix. And these are some these are Raman spectra, these are FTIR spectra, and this is TGA. From there we can see around 10% ZVI can be easily incorporated into this polylactic acid matrix. And this is the TM. From that TM you can see that when it is simple ZVI nanoparticles, how they are agglomerated with each other, it is clearly visible from the TM. But when they are present in this polylactic acid matrix, sorry, when they are embedded into this polylactic acid matrix, you can easily see how they are nicely dispersed. They are not so much agglomerated. Okay. So from this EDX spectra also we can see that iron is present in this polylactic acid encapsulated ZVI particle. Let's see its performance. Now when it comes for the performance, we have taken two model contaminants. One is methyl orange, another is TC, trichloroethene. That is water insoluble contaminants. You can call it as NaPl, and methyl orange is a water soluble dye. So you can see that for TC, that is the trichloroethene, For trichloroethylene also, these particles can slowly release ZVI, and then TC can be completely dechlorinated. Percentage of the dechlorination of TC, you can see that it is going on over the time, and then concentration of the right, this is a methyl orange. This is for TC. This is for methyl orange. Methyl orange degradation was even much faster than TC. Of course, this is water soluble dye, so it will be having that very easy access onto the surface of the ZVI nanoparticle, which are present onto the polylactic acid surface, and automatically dye disappearance or dye degradation was very fast. But TC also, with a significant reduction of TC was observed within a 40-45 minutes. That is in the batch reaction, means when we wanted to see whether they are working or not. But then what we wanted to check, whether if there is a sand there, whether they will work or not. That is the actual subsurface environment. So in presence of sand also, they were quite working. And so this is just a methyl orange and sand as a control we have tried. So no reduction of methyl orange, you can see. So of course ZVI releasing and coming out, and that is doing the reduction. So in presence of sand, it is even faster. You can see that in presence of sand, it is even a bit faster than without the sand. Okay. Sorry. This is in presence of sand, that is a bit slower compared to the just simple water. This is just a simple water, and because this bar was covering, so I couldn't see. So now, so in presence of sand, you can see that. So definitely it is working, but a bit slower than the simple water, because of that interference of the coming from the sand. Anyway, but still it is working quite well. But as a control also, we have what we have done here. So it is just a simple ZVI when we have added. It is not really a bit reduction of the concentration we can see, but then over the time ZVI immediately lost its this ZVI is like we kept it under storage for 1 day, and then we tested, and then ZVI completely oxidized, so it didn't work. And only PLA, of course, naturally didn't work. So what it is telling, when PLA along with ZVI it is there, it will work. So here what we are trying to show, when we are using in a column, so that is exactly simulated to the subsurface environment. When you are using them into the column, through the columns, particle will transport to the ground where it's supposed to reach. And then you can see that around 40-45 days, the particles were still active. Until 40-45 days it took that sand column to reach and then completely remediate the water, whatever the concentration we have started with. So it took around 45 days to completely remediate the water. Okay. So this clearly says that, when you are having a particles ZVI inside the polymeric particles, definitely it has a it will have a prolonged stability, and it will slowly release ZVI, and it will work. Okay, so this is the summary from this work. So that PLA-based microparticles entrapped with ZVI, which can be fabricated in a single step by electrohydrodynamic jetting technique, and it can potentially act as a slow release reservoir to remediate groundwater contaminants, both hydrophobic and hydrophilic. But storage stability can be vastly improved, like 1 month it can be kept in the open air, because of the polymer coating is there, as compared to the bare ZVI, just 1 day it's gone. And these particles were found to be recycled up to 4 cycles. You can see that up to 4 cycles, that particles, the same particles after using, again if you can recycle, it can be recycled up to 4 cycles. But 5th batch, there is no activity, so all particles might have, the ZVI might have come out, or mostly it got oxidized, whatever leftover was there. So now what we have learned that when you have a JVI inside the polymer particles, it is quite active and it can remediate the groundwater, and it can work as a slow release reservoir, which is very important for the groundwater application. But what is the cons it has? These particles lack prolonged dispersibility in water. So the problem is it's all a hydrophobic. It's isotropic particles, means it's a completely hydrophobic particles. So when all are hydrophobic particles, initially if you just disperse them, they will stay. Then over the time, they'll just come together and then they will all settle down at the bottom. So automatically you always have to be under agitation or stirring condition, otherwise they will not be dispersible. And also, when there is an application, when you need this particle to work at the interface to catalyze the degradation of both water soluble and insoluble. So for example, if I add methyl orange and TC all at the same time, that is a real scenario in the groundwater. So the water soluble and water insoluble, both contaminants are there at the specifically at the DNAPL dense non-aqueous phase liquid. At that stage, you need to have your particle which can stabilize this water and oil interface. If your particles work like a surfactant, here comes that colloidal surfactant concept. So if your particles work as a surfactant so that it can stabilize the interface between the water and oil, then at that juncture, this particle can degrade water soluble as well as water insoluble contaminant at the same time. So how can you get that with this kind of isotropic particles? Now here you have to move on to this anisotropic particles, and then that's why we have done this next work that is all based on this particles which will have an anisotropy in nature. That means one side would be hydrophobic, another side would be hydrophilic. As I said, you cannot jet particles having one compartment hydrophilic and another compartment hydrophobic. But what we realized, you don't have to make the whole compartment hydrophilic. You just have to make the surface of this compartment hydrophilic so that they are good enough to disperse them in water, and whatever water soluble contaminant will face this only one of this compartment and they can be destroyed by iron nanoparticles. Okay, so or any other metallic particles. Okay, so thinking that what we have designed a bicompartmental particles having one compartment hydrophobic, another compartment also hydrophobic, but on the surface of those compartment, surface of one of the compartment, we have decorated with a polymer brush. So polymer brush is a hydrophilic brush. So the hydrophilic brush will help it to disperse in water and can stabilize this oil water emulsion. So you can see with this oil and water emulsion at the interface, these particles can go and these particles can actually stabilize. This is all water, these are all oil droplet. So this oil droplet can be stabilized by this Janus type of particles, which will have both hydrophobic, hydrophilic characteristics. Okay, so if we can have this, whatever the contaminant inside the oil part can be taken care of by this green compartment, and whatever the contaminants present in this water part can be taken care of by this brush compartment. Okay, so that was the idea. So we wanted to make a Pickering type emulsion. Pickering means solid particle stabilized emulsion. That's called Pickering emulsion. And with this, we wanted to design this kind of Janus particle so that we can remediate the water as well as water insoluble contaminants. Okay, so there are very different kinds of application for this anisotropic particles, as I have already mentioned. Now let's move on to what we have actually done. So what we did, we have again used the same technology, electrohydrodynamic cojetting technique, where one side is polylactic acid, another side also polylactic acid, but very few percentage of this special polymer, we call it poly MMA BEMA. Okay, so what is this BEMA? BEMA means this has a small bromo initiating moiety. So this bromo initiating moiety is actually can be used to grow polymer brush by a controlled radical polymerization like ATRP, atom transfer radical polymerization, and you can have a brush only from this one of the compartment where this bromo initiating moiety is there. Okay, so with this we have made three different kinds of particles, means a different composition. P10 means where you have this 10% of this bromo initiating moiety only in this orange compartment. For P25 same 25%. P50 means 50% of this bromo initiating moiety. So what we are trying to do here, we are changing the initiator concentration from P10 to P50, increasing the initiator concentration so that we can get a high dense brush only in one of the compartment. So brush density, if you want to vary, we have to vary the initiator density. That's what we have done. So by electrojetting, you can see the nice spherical particles we can make, which are bicompartmental in nature. And then once we have this bicompartmental particle only initiating moiety in one side, with that we have used a hydrophilic polymer. This is a monomer called DMA-EMA, dimethyl aminoethyl methyl methacrylate. So this DMA-EMA monomer can be grow selectively from one of the compartment to have poly DMA-EMA brush, that is a hydrophilic brush. Okay. Now, so these are the some characterization. You can distinguish, see that we have made this bicompartmental particle from the confocal images. It's a very clear they are bicompartmental is nature because we have put two different polymeric dye to image them and to show them they are bicompartmental is nature. Now after once we have, this is after jetting, you see the particles looks all similar spherical particles. Now after ATRP means after you do the polymerization from one side, 10% you don't see much change, 25 also difficult to see, but 50% you can see one of the, this looks like a core, that is one compartment remain unchanged. Another compartment you can see a good swelling environment, that is a brush, a hydrophilic brush that is all in water. So it hydrophilic brush got swollen in water and you can see that nice brush covered compartment in one of the particles, one of the compartment of the particles. Okay, so now when you check that particle size along with more and more initiator density, you are changing automatically. So particle size also increasing because the polymerization over the polymerization, when the initiator density higher, more dense polymer brushes will grow and it will become more swollen and the size will be enhanced. Okay, so now with the polymerization time also, you can see that polymerization time, more and more polymer chains will be increasing, so automatically size of the particles also will increase. Okay, so this is just a FTIR to show that we have successfully modified the particles with this DMA-EMA polymer brush. And these are the particles before SI-ATRP. You can see, so everywhere it's a uniform particles, and then after SI-ATRP, one side of the particle you can see that smoothened. So that is basically because of the polymer brush. Okay, and then for confocal also you can see in the 0 hour very small particles, and then 15 minutes it is increasing, and 30 minutes one of the compartment, that is blue compartment, it's increasing, and here after 1 hour you can see that nice bicompartmental particle where the blue compartment kept on increasing. Okay, so now particle size by varying the grafting density, that I have already shown. When you change the polymerization time, when you change the monomer concentration, when you change the initiator concentration, many ways we have seen that the particle size continuously increasing and one of the compartment kept on increasing, and you can see a swollen brush after 1 hour. Nice swollen brush can be seen in one of the compartment. Okay, so after 30 minutes, there is hardly change of any particle size because the brush now dense and good enough, so you cannot see the change of particle size anymore. So how these particles, one side hydrophobic, another hydrophilic, how they can be used as a Pickering emulsion stabilizer. For that, we tried with this P10, P25, P50 different, and we have taken water and oil, in this case water and octanol, those two phases, and then we use these particles as a stabilizer. You can see that 10, 25, 50, all of them can stabilize the emulsion, and especially for P50, that emulsion was stable for more than few months. So the emulsion were quite stable. And when we wanted to look at how those emulsions look under optical microscope, you can distinctly see that these particles having this hydrophilic and hydrophobic nature, bicompartmental particles, they are actually stabilizing this water oil emulsions. So nice emulsion and stabilization pictures you can see clearly from these optical images. Okay, also we have wanted to check if we add a water soluble dye, how they look like. You can see that the particles is completely covered with a water soluble dye, because this outside is the hydrophilic, and so hydrophilic dye will be completely covering, and that clearly says that emulsion is getting stabilized by this biphasic particles. Okay, so now,
Sorry to interrupt you, ma'am. Can you please wrap up your talk?
yeah, 2 more minutes, I will finish.
Sure.
I don't know why it is not moving. Okay, so these are all pH stability. So these particles are pH responsive too. Now what we wanted to have this particle used for water remediation. So one of those compartment we use the iron nanoparticles. Another of this brush we have modified with gold nanoparticles, so that both the metals will work in their own compartment and will remediate the water. So that was the idea, and these are few characterization to show gold selectively present only in the brush modified compartment, and then through the TGA, we can actually find out how much gold concentration and how much iron concentrations are there. And then through the different TEM images, you can see one side of the compartment has this iron nanoparticle, another side surface of this compartment has this gold nanoparticles. Now, so once we successfully characterized these bifunctional particles having both the gold as well as iron nanoparticle in both, this is gold, green one, and iron is the red ones. Mostly they are predominantly present in two different compartments. And then what we wanted to, these are all characterization to show they are present in two different compartments. This is gold, this is iron. And now once we have done that, we have done the catalysis, and you can see that water soluble degrader, say for example nitrophenol, paranitrophenol can be reduced to para-aminophenol in presence of gold nanoparticles and sodium borohydride. Within 1 minute, you can see that these particles are able to completely reduce this para-nitrophenol. And then for iron nanoparticle, which are embedded inside the hydrophobic zone, and then so it takes more time. So it takes around 7 days to remediate the water, get rid of this trichloroethene. So with this, I would like to finish my talk. So what we have learned here, so what we cannot achieve from isotropic, we can achieve from these anisotropic particles, and having hydrophobic, hydrophilic compartment, and remediate both water soluble, insoluble contaminants presenting at the interface of water and oil. Okay, so with this, I would like to finish my talk, and we are here at IIT Delhi. Please visit our website. This is our group, and we are very thankful to Amity to give us the opportunity to show our work. And all these works have been heavily supported by DST and ICMR and SCRB and other government funding agencies. So if you have any questions, I'll be happy to answer. Sorry, I took so much of time. Yeah, please.
Thank you so much, ma'am, for wonderful talk. Any question from audience?
Thank you, ma'am. Thank you for the wonderful talk. And it's an excellent presentation and excellent publications you have. So first of all, I thank you for accepting my invitation. And we would really like to hear more from you in physical mode sometime later. I have some quick questions from you. I know
Sure,
that
sure. Just a second, just a second. Can you please help me how I will come out? Achha, now I know. I think I have come out from this because I cannot see you.
Okay, you have to, yes.
Yes, yes. Yeah,
So,
now I'm comfortable. Yeah, please, please.
yes. So the shell that you, I mean, the encapsulation that you've done with PLA and all. So I think the thickness also matters.
Sure, matters.
Right. So you showed around 40 to 45 minutes, the particles started probably reaching or releasing from that encapsulant. So
Yes.
is it due to their micropores, or what are you trying to control? Is it the thickness or the micropores?
So basically you can control all of those, okay? So that technology we have, but currently for that particular application, what you are showing, that is not the thickness there, we are controlling via pores. And there are two mechanisms. One is that this is a porous particles. Pores are helping the water to go through and get the jet to come out, okay? So that is osmotic pressure difference which is making them to come out. And on top of that, polylactic acid being a biodegradable polymers, they have also over the time started degrading and then making that water to go through them, making the water make a channel, and so that the iron can be coming out much easily, okay?
And I know making this genus particle is really tough. So you must have worked really hard to optimize these genus particles. So
Yes.
The polymeric brushes that you're talking about, so is it possible, I mean, you are able to have them only at one part, or they actually can be coated, or I would say adhere on separate parts of globules?
No,
I mean,
no, we can. We can. So let's say you make a 2 compartment or 3 compartment, and each of the compartment you can patch it with any other functional group or any other moieties if you want. I have shown only 2 compartment, 1 compartment you are patching with brush. So you can patch with, and actually you can make as many compartment as you want if you can, and then all of the compartment you can patch it with very different functional group, and you can do it. It's feasible.
yeah, and you have shown so far with I mean, coating gold nanoparticles and
Yes.
iron. So this
Yes.
is the focus is mainly for contaminants like soluble contaminants, or it has been, I mean, I mean, it must have been a big project, right? You've been working on.
Yeah, but yeah, the focus was on. So when you have a dual metallic particles, they have their individual domain to work. Can you put them together and work them simultaneously? That was a question came into my mind. And then this is the way I thought, if I can put one in this brush domain, they will be very much accessible in water area, water soluble contaminant. They will be highly accessible for those gold nanoparticles, okay? And then other iron, if I put them in the hydrophobic zone, and then automatically hydrophobic contaminants which iron 0 can get rid of, that can also be getting rid of by using our polylactic acid releasing iron 0 particles. So that's why we have put those two metallic particles and let them do their own work at the interface between the water and organic. Yes.
Thank you so much. I'm sure I will be talking to you later also, discussing more about you.
Sure.
So I
Sure.
think, Kirti, you can take some of the other questions in the chat box.
Yes, ma'am.
Sure.
Ma'am, there is a question from Arpita Bhattacharya. What is the size range of zero valent iron nanoparticles? Can magnetic nanoparticles like iron oxide can be used instead of zero valent iron nanoparticles?
Okay, so the size what we have, it is around 50 nanometer, 40 to 50 nanometers. You can even reduce, go down to till 20 nanometers, but what we use is around 40 to 50. Okay, and zero valent iron is well known to degrade the water soluble or insoluble contaminant. That's why we have chosen that. Iron oxide, of course, you can encapsulate them using the technology what I have proposed, but iron oxide degradation is much less efficient compared to the iron zero. So if you want to image them like imaging agent or MRI contrast agent, then people do encapsulate iron oxide, and that is a very different application, but you can do that.
Okay, thank you so much, ma'am.
Thank you, Dr. Sampa, for this wonderful talk and for highlighting issue of conventional method for this water remediation. I completely agree with you that nanomaterials can play an important role to overcome this problem. And as you showed that different anisotropic colloidal surfactant can help in the water purification. So thank you once again, ma'am, for the wonderful lecture.
Thank you. Thank you for calling me. So
Thank you so
hopefully
much.
one day I'll be able to go there.
Sure, sure. We'll invite you soon for a physical talk. In fact,
Yeah.
if you see the chat box, there are many compliments for your talk.
Okay, okay. Thank you so much.
Thank you. Thank
Okay,
you.
okay. Bye.
Bye.
Now it's time for a break. May I request all the participants please attend our post-lunch session sharp at 2:30 p.m. Thank you all. Informative and provide the participant with enormous knowledge on various aspects. Now in this session, Ms. Shingika Soni is going to coordinate with me. In the post-lunch session, we have the 5 speakers. Our first speaker is, just give me 1 minute, I'm going to share. Yes. So our first speaker is Vandana Luthra, professor from the Gargi College, Delhi University. Dr. Vandana is working as a professor in physics at Gargi College. She has availed prestigious voice cast fellowship from the DST to work on the gas sensing material at University College London, UK, and Raman Fellowship at State University of New York on the development of nanomaterial for energy applications. She has been a visiting researcher at UCL UK. She has been a recipient of the this meritorious teacher award by NCT Government of Delhi. One of the 4 digital literacy champion by campus of Open Learning University of Delhi, Edinburgh College, Scotland, and visiting the Edinburgh College, UK as a part of the program. She is a recipient of the Indian Association of Physics Teacher Deenbandhu Sahu Memorial Award for the year 2017. She has completed research project funded by DST, UGC, 3 innovation project by University of Delhi. She has received Teaching Excellence Award and Innovation and Best Innovation Idea by University of Delhi for one of the innovative project GC 204. She has completed UGC UCARI Thematic Partnership Award, which facilitated exchange of faculty member and 4 PhD scholars from India and UK on the development of nanomaterial-based gas sensors. She is also engaged in organizing a range of activities under a Science Society grant under the agency of the National Academy of Science India Science Society program. She has published more than 33 papers in very reputed international journals, 7 book chapters, e-lessons reviewer with the reputed international journals, editor, board member, and physics coordinator for Star College scheme in her college. The title of her talk is Climate Change from Cause to Technology Mediated Solution. Vandana ma'am, please.
Yeah, thank you so much, Dr. Nidhi. And I must, on the onset, I must thank Dr. Balwinder Shukra, that is the chairperson, Dr. O.P. Sinha, Professor O.P. Sinha, and all the faculty members who have organized such a meaningful workshop, Dr. Ranu, Dr. Nidhi, and Dr. Mittal. And my greetings to all the esteemed participants, faculty members, and the students to share, which has given me this platform to share my, I would not say something very great. It is just sharing of my knowledge, but I have gained over the years. And the topic is so important and close to my heart because whatsoever research we are doing, that should be for the society. And this particular workshop is actually fulfilling that theme very well. So let me share my screen, just a moment. Is my screen visible?
Yes, please go to slide
Yeah, I'm doing that.
Yes, visible.
Yes. So very interesting topic, climate change from causes to the technology mediated solutions. And here I would like to give glimpses of my college, which is situated in the South Delhi, one of the premier college, women college in the South Delhi, which caters to sciences, commerce, arts, and humanities. And this is accredited A by NAC, and it has got a star status by Department of Biotechnology and NIRF rank 16 in 2021. So this is an aerial view of that, and one can see it is in the South Delhi, and we are close to IIT Delhi and AIMS, and very many prominent institutes are nearby. So just a moment, let it go. One can see the greenery around. There is a perfect ratio of greenery as well as the covered area. So that is really interesting. Yes. So I move forward. The 5 elements of, let me minimize this just a moment. So the 5 elements of Panch Tattva would say that don't dismiss the elements. Water soothes and heals, air refreshes and revives, earth grounds and holds. Fire is a burning reminder of our own will and creative power. Swallow their spells, and there is a certain sweet comfort in knowing that you belong to them all. These words by Victoria Erickson give us an importance that on this planet Earth, which is blue planet and is unique in Earth, we have to work dedicatedly for the purity of these elements, which are air and water. And climate change, and is there any connection between the pollution of air or water? Are they interconnected with the climate change? And there are many such examples which pose challenging problems to the sustainability of life on this unique blue dot, and hence are a cause of utmost attention for mitigation through various technology-mediated solutions. And when we talk about this, the outline of the talk is centered around these points. So I will be just showing an overview of climate change, causes, impacts, and assessments, interdisciplinarity and need for climate change education as a cross or trans interdisciplinary subject rather than just a standalone subject, and the technology mediated solutions which can be also obtained by nanotechnology and nanomaterials, and future directions and way forward. So the talk is also aims at sensitization, awareness, and possible solutions for combating the climate change, thereby minimizing its adverse effects. To make this session more interactive, I would be using some interactive tools which will be displayed, and some may find these also useful for interactive sessions. So here, warming up activities there. So kindly join using the following link. May I request Dr. Ranu to kindly share the link in the chat?
Yes, afterwards.
So you have to just, all the participants, please join using this Slido, and that the code for joining is 1999 5 times 9 199999.
Can you repeat again? 1999
5 times 9.
I've written in the chat box.
Yeah. So just write one word which describes the climate change and its causes. My Slido is now active. So is my screen visible, yet visible?
Yes, ma'am.
Yes.
So it is 199999. Is it visible?
Yes, yes, it's visible.
Yeah. So all of you are just have to join using this and just put the code 199999. And one participant is typing any cause. Don't write the code now, just write one word which according to you can be a cause for the climate change. Only 2 people have joined, 3 have joined. Please, those who can join, it is not mandatory that everyone should join. Those who can join, please do join. So global warming. So according to you, global warming is a consequence actually. So the causes of climate change. Technology upliftment. Somebody has written technology upliftment. One person has written global warming. Please, more responses. Fossil fuel. Perfectly all right. This is a cause. Deforestation, yes. Some more answers, yes. We have got another point as industrialization, very well written. Is my screen visible? Is it visible to everyone? Whatsoever is being typed by people?
Yes, ma'am.
Okay. More vehicles, right? Carelessness. So I would say we need to change our attitude and we have to be more sensitive towards issues which are surrounding us. Plastics. Can we have some more words and then we can move forward? Air conditioners. So one can make an essay of these that the human activities are more or less responsible and are the probable cause or the cause for these kind of things which we are witnessing on our planet. Okay, moving on forward. Now I would be interested to know what are the evidences which we are having which are giving us this indication that the climate is changing. We are saying that climate is changing, but how do we know that it is changing? So this is another, you can write just one word or few words to just describe what evidences. These evidences could be something nearby our town or within city or within world, any place on earth, anything which can tell us that climate is actually changing. So one answer is very pertinently come, that is extreme weathers. Are we observing in Delhi that there is hot temperatures are increasing, or is there any other increasing summer temperatures occasionally, and abrupt weather and extreme weather? Some more answers can also be there. So floods can come under the extreme weather. More breathing issues. reduction in rainfall in some areas. So can we say in some places reduction in rainfall is occurring, and some places there is abundance of water in the form of in the form of floods, melting of ice caps, right? Melting of ice cap is evidence of global warming, and global warming would mean that the temperatures are rising, and that is causing the ice caps to melt. Change in seasons. Change in season is also affecting the crop pattern, and that is affecting the, say, many other factors are related to that. So that is also something very serious. Hazy night sky. Hazy night sky would have exact meaning I'm not able to make out, but yes, the pollution levels are changing. Pollution levels are also one of the reason for these kind of things which are happening. Okay, so going back to my slide. Thank you so much, everyone who all have participated. Very keeping us on toes after this. So let me again come to the slideshow mode. Yes. So here air pollution is also one of the cause. I will not be able to cover all the causes because it is not possible to go in detail and complete everything. But as a case studies, we may take some of the causes and how all these are affecting these. So one of the case studies, air pollution, the presence of entities in the air which have harmful or poisonous effects to human, plants, animals, and the environment. And according to a WHO report, 9 out of the 10 people breathe air that exceeds WHO guidelines, and that limits containing high levels of pollutants. So high level of pollutants is something which is a matter of concern for all of us. If we try to see the death rates from air pollution in the year, say 2017, and here the death rate would mean that these are measured as a number of deaths per 1 lakh population from both outdoor and indoor air pollution. Rates are age standardized, meaning they assume a constant age structures of the population to allow for comparison between countries over time. And one can see a contrast from the lighter, say, color to the, say, darker color, and in that the areas which are in red or in dark orange are of concern because there the death rates are even much more than the rest of the areas. And moving on further, what are some of these pollutants? When we are talking about these pollutants, these are particulate matter, which could be PM10, PM2.5, and PM1 is also being measured these days, and which is even all the more dangerous, and more studies are needed in order to quantify that effects. Carbon monoxide and carbon dioxide, ozone, VOC, those are volatile organic compounds, nitrogen oxide, sulfur dioxide, methane, and PAH, that's our polyaromatic hydrocarbons. So if we try to see that these are the pollutants, and some of these are a part of atmosphere of Earth and its composition. So if we try to see the composition of the Earth, the majority of the gases, it means that 99% of the gases are composed of nitrogen and oxygen. And there is a composition of gas which is below 1%, which is composed of argon, and it is also has got carbon dioxide in ppm level, and ozone, and others elements are there like CO and N2O. So why the concentration which are there in the very small amount, which are called trace gases, are so critical for the Earth atmosphere? When we are not talking about, say, we know that now the atmosphere is such that it is oxidizing, we all can breathe, and we all have different components of life sustainability on the Earth. But why the gases which are 99% are not more, are not of concern, but and the gases which are in the trace amounts are so important? So we have to understand that also. Like if I talk about carbon dioxide, it is in ppm level. Ppm level would mean parts per million, and it is of concern. Why? So that case is there. So we will introduce, all of us are aware of a term called greenhouse gases. And why these trace gases are so important? Because for the many years now, there is a correlation between their amount and the human activities post-industrialization. And all of you, those who answered, also have indicated that industrialization and the many other activities like burning of fossil fuels and agricultural activities are responsible for enhancing the concentration of these gases on the earth. And the amount of methane has increased, the amount of carbon dioxide has also increased, and carbon dioxide is again plays a very important role because it is available in the dissolved forms in the oceans also, and it is 60 times more say carbon dioxide in oceans than in atmosphere, and it keeps on slowly being released in the atmosphere. So there is always a balance has to be there between the one which is available in the atmosphere as well as in the oceans. And there is a concern of having runaway greenhouse effect on the earth, and that will cause more and more melting of ice in the Greenland and Antarctica, and will cause sea levels to rise. And the principal absorption of these emissions lie in the range of say 5 to 7 micrometer, 14.5 to 16.4 micrometer, and greater than 22 micrometers. So why these absorptions are so important for these gases? So these gases, these entities are entities which are heteronuclear, and they are able to say absorb long IR radiation. And if we assume the earth, if we all know that the earth behaves like a black body radiation, and the kind of radiations which will be emitted keeping its temperature around 300 Kelvin, those will be in the long IR range. So that, and those are the source for the radiations which are absorbed by these greenhouse entities which envelop our atmosphere. Moving on further, if we try to see the heat budget of the earth, then the amount of, if you see to this picture, this has been taken from NASA. If you see the light and the heat components, then one is shown in say yellow color, another one is in orange. So incoming solar radiation is approximately 340.4 watt per meter square. A part of it is directly reflected by the clouds, and that is approximately 1/3 of the total which is incoming. Now, if the cloud dynamics changes because of the change in the aerosol amount or because of any other reason, the amount of heat which will enter to the earth will be more, and it will be less reflected. In that case, the clouds are playing a very important role. And the overall heat budget, if I have tried to explain this further by another figure by Forbes, one can see that the total from the sun is 340.4 watt per meter square, which is, and a part of it is reflected back into the space, which is approximately 1/3, and that is also called the albedo of the earth. And the earth's atmosphere, which is comprising of these gases, which are greenhouse gases, that acts as an insulating envelope on the earth, and they are able to retain heat. If their amount increases, then like when we are on the cold day, we take this all sorts of insulations just to trap heat. The same purpose is being done by these gases, and if their amount increases, there is rising temperatures could be attributed to that. So this heat budget would say that right now we are having a balance, that the net gain, which is incoming and outgoing, the net gain is 0.6 watt per meter square. If this net gain changes, if this increases, like if the amount of heat which is coming and that which is going, there is this deficit keeps on increasing, then in that case, what will happen? The overall temperature of the earth will increase, and then that will have very many different consequences. So moving on further, that what kind of consequences would be there? One can talk about albedo. Albedo is defined as the reflectivity of a surface or an object which can take values between 0 and 1. So it is also called whiteness of a surface. It is expressed as the ratio of energy reflected in all directions to the total energy incident. Each surface has got a different value of the albedo. Like for ice, if it is ice, it is 0.7. If the ice is fresh, it is 0.8. If it is the smooth cloud tops, it is 0.8. And if the sun is at zenith, then it lies in the range of 0.02 to 0.04. For grasslands, for desert, it is 0.2. If we try to take a collective amount of this And its value also depends upon the type and the nature of the clouds. We have different nature of the clouds depending upon what height they are being formed and what albedo they have. So if we say take an average value of the Earth, it is 0.33, and it changes for each planet also. So right now there is a balance, which is energy budget balance is there. And if the temperature of the Earth will increase, nature of cloud will change, it will also change. There will be more and more say melting of the ice, and it means if ice caps melt, what will happen? And there is a very strong evidence by all the satellite images and all the data which is being collected that the ice is melting, our ice cap are shrinking. So in that case, there will be the amount of heat which will enter the Earth will be more, and that will cause say thawing of the permafrost. Permafrost is a frozen layer which has been there on Earth for at least 2 years. And if that permafrost thaws, it means that all the organic material which is embedded in that will also be thawed, and all those are emitters of particularly methane and other greenhouse gases. So what will happen then if this process keeps on going will be really, really drastically dangerous for Earth. We have an example of greenhouse effect on other planets also. Like Venus is a very, very live example of that. Venus has got has got area as well as size equivalent to that of Earth. Like it is also called twin Earth with an ill fate, because of the runaway greenhouse effect, the temperatures are quite high. There is a temperature anomaly. Like it is otherwise a second planet from the sun. It should have a temperature which should be intermediate between that of Mercury or say Earth. Earth is an habitable zone, but in the case of Venus, the temperature is much higher. It is 430 degrees Celsius or in that range, and it is not inhabitable. So in that case, there are live example of the runaway greenhouse effect on Venus, and which gives us an indication that this can happen to any other place where this amount goes in from a say stable greenhouse effect to a runaway greenhouse effect. On Mars, there is a very weak say atmosphere, and there is a very thin Martian atmosphere, and this effect is very weak. But Titan is a moon of Saturn which has got a lot of very large concentrations of methane, and there also people are studying the effects of these gases on such planets. And in some other planets also, the likelihood of methane and other greenhouse gases may change the dynamics of that cloud formation, other things on those planets. So if we try to see the case of Venus, Venus is superficially very much like Earth, atmosphere, but atmosphere is 96.5 carbon dioxide, and surface pressure is 90 times that of the Earth, and it has lost all its water and hydrogen and escaped into the atmosphere. And at this pressure, carbon dioxide is highly absorbing at 15 micron, leading to a temperature of 730 Kelvin, which is in the range of say 400 at 30 to 460 degrees Celsius. So these are the examples which we need to consider when we are talking about the effects of the greenhouse gases drastically getting enhanced, more and more enhanced on Earth. And there are interconnected factors. So when we try to see the climate change and the association with these gases, one can see that atmospheric carbon dioxide was never like this, even if we see million of years back data. But one can see from afterwards, this 1950, after the post-industrialization, there is a drastic increase in their amounts. And though the levels are in ppm range, but there is an association between the activities, human activities, and increase in these gases and the temperature on the Earth. So that is why these are very important from the point of view of say sustainability on Earth. And what are the major sources of these emissions? We all already know, we are very aware of these facts, that transport, agricultural, industry, waste is one of the largest source of methane. And there are different resources available which say that 13% landfill waste is cause of so many these many gases which are greenhouse gases. And more particularly now, there is very difficult to find even the landfill say places on Earth, because the kind of and there are a lot of work being done in engineering the landfill site, so that the gases are not emitted. There is a usefulness of these gases for other activities, like for biogas and other sustainable things come out of those, rather than just becoming a waste site, which is a source of so many, say, diseases and so many other greenhouse gases. So and these the public health is also related to all these environmental impacts of these pollutants on Earth. One can know that these are all diseases are also come out of when these gases emanate from in the atmosphere. So preventive measures and mitigation would mean that what precautions, preventions can be taken for the mitigation, reduction in the responsible causes, mitigation strategies, and interdisciplinarity. Climate change education. This has to be integrated with the different subjects which we are studying, and there is a use for research for solving societal issue, which is very much pivotal in these days in orienting our research work. And it is I must say that this topic itself is so meaningful. As I told, this is very close to interconnection of the society and the use of research and use of technology for our issues which we face on a day-to-day basis. And if we see the interdisciplinarity, and I take a case of air pollution, if I say air pollution is producing aerosols are being produced, and they are causing air pollution. Then if we try to see the properties of aerosols, then we talk about say meteorology, atmospheric physics, chemical engineering, physics, and electronics and computer science, and mathematics and statistics also, if we try to talk about their modeling or monitoring or measurements. When we try to see their effects are like different diseases such as respiratory, cancer mutants, and stress and neurological effects, psychological effects. These all happen because of that. And these are topics of mental and psychological impacts. Like if we talk about people working in factories, having indoor, very deteriorated indoor and outdoor air quality, mining sites, and in the households also, in the kitchen also, ladies especially are prone to so much of vapors which are coming, and in some places they all are working in a single room, and it may happen to anyone, those who are working in those conditions, to have mental or psychological pressure which is coming out of these adverse conditions. And when we are talking about aerosols, these are the nucleating sites for the cloud formation. And we just saw the clouds are playing a positive and the negative role in the case of heat budget of the Earth. And when we talk about the consumer market or the commerce, then this policy making and industrial processes are also playing an important role. And there is a need that we need to reduce the carbon footprint. And when we are talking about the carbon footprints, then in that case, the government policy agreements or the political science also plays a very important role. And these pollutants are sources of the greenhouse gases which are altering the heat budget or the energy budget of the Earth, and are contributing to climate change. In the case of future targets, there has to be technological innovations which can provide us materials which are more efficient, materials which are producing less carbon footprints, or materials which can be used for enhancing the performance of a particular process. And in that prediction and modeling, these days, artificial intelligence and machine learning is also being used in different fields. Its use is now, I think, inseparable for applications in multiple fields. And when we are talking about data collection or visualization and analysis, data science or mathematics and statistics also plays a role. So I assume that this slide is giving us flavor that this field, any field we take, has not to be studied in isolation. It has to be interconnected, and it is interconnected actually, and it has to be taught, or it has to be seen in purview of with an integrated approach. And here the data collection, correlation of various parameters, case studies, data analysis and validation, all these are also needed in order to formulate effective policies and which affect all of us. This figure has been prepared using Kaggle, and I acknowledge that resource for that using. When we talk about the sources of data, so if we are talking about, we have taken air pollution as a case, and the data is being monitored by, in India, it is Central Pollution Control Board, and each state has got different boards where the data of different particulate matters, different gases, the temperature, all this data is collected. And also WHO, one can always go to this reference and try to see how this data is being collated for all over world and helps in formulation of different policies. So now, combating the climate change is something which is now going to, I will be going to the second part of my talk, and that is we have to make choices for fuels and the mode of transport in a manner that these effects are mitigated. Waste segregation is something which has to be done, and waste reduction strategies can be done at individual also. I see that we are also in a habit of this habit has emerged over the years, like we buy new things and there is in lack of more say, if we can't repair something, we just throw it. And so I feel if there are more repairing centers, it may also cause reduction of the waste and the monitoring of the greenhouse gases. And in that, technology mediated solutions can be achieved through different methods, and those through different methods are here. Technology or the material plays a very important role in finding solutions. So here the assessing, measuring, or monitoring and reduction and implementation is done. If we see again the example of air pollution, we are monitoring the gas concentration in atmosphere at different places. Simultaneously, temperature is also being measured, and we can also do the water treatment at various levels can also be done. And in this case, the materials play an important role in enabling that technology, and technology and materials go hand in hand. If we see the example of bulk materials and nanomaterials, so I think it is clear because this is an Institute of Nanotechnology, and each participant or majority of the participants must be aware of what nanomaterials are, what advantages they offer in comparison to bulk material, and how they are synthesized. All these must be aware by all of you, so I can skip this part. But here I would only like to highlight few things, that they offer more surface to volume ratio, enhanced functional properties, and applications. Like one is always studying when these field was introduced. This has been in existence for over many years, but it through the advent of technology, now we can view their sizes, we can see the morphology, and so many other things are possible. And we can see and compare their properties as compared to the bulk materials and see their enhanced applications. And those applications find place in as a gas sensors, as energy efficient materials for wastewater treatment, and so many other immense applications are there. So I would be considering example of nanomaterials for gas sensing applications. So can I just get to know how much time I have? I think it is 10. I have 15 more minutes.
Yeah, you can.
Yeah. So if we see the data being taken by CPCB and different state agencies for the pollution, then there is a monitoring over a particular place is done. There are different stations through which the data is collected, and it is being monitored. And there are some manual stations, there are some stations which are automated. So the data which is being collected is of different gases and particulate matter, as I have already described that. So different gases would mean NO, NO2, NOx, ammonia, SO2, CO, that is carbon monoxide, ozone, benzene. There are other materials also like benzene, toluene, and so many other things which are being monitored on a daily basis. One can always do research on that also, because data is available of different stations, and one can download that data. One can try to see the trends and how the trends are changing over the time. All these analyses can be done. If I talk about the Delhi CPCB, then these stations are in Jahangirpuri, Sirifort, Anand Vihar. From previous times, now the number of stations, these are just illustrative example, but now the number of stations are very many. More and more sensors are being deployed for the monitoring, and considering the following parameters, PM 2.5, this all I have already explained. And so if the data is taken for a 1 year of different pollutants, one can see the trend. This is the data of Sirifort area, where my college is situated, and one can see that PM 2.5, PM 10, NO2, SO2, CO, and other factors like ozone, these are monitored. And then these are patterns are analyzed, like how the pattern is changing over the time, and how evolution is happening. Like there was one study which said that in the COVID times, the air quality got improved, and there was lessening of the temperature of the different cities also was there. There were a very, very positive effect on the environment. So it means that if we control the human activities, we can try to reverse the effects which we are habitual, and we do just there was one word, carelessness. If we all are made aware of the impacts, if we try to understand this in all these in an integrated manner, I think we will be more conscious, and our behavior change will also be one of the contributing factor towards this. So if I try to see about the gas sensors, the aim would be like for I think this point is clear. For monitoring of the climate conditions or the weather conditions, the gas monitoring is done by different gas sensors. So our aim would be to understand what are gas sensor, what mechanisms are followed to which aid in the gas sensing say activity, how do these works, what are the key features, how these are fabricated, and monitoring of different gases. I would like to say here that it is very, very difficult task to know that which gas sensor will work best for which particular gas at what particular temperature. All these are a matter of research, and students may find this field interesting. And I will be also sharing some research papers which will be helpful to them. So the outline of the second part of the talk is background about the sensors, familiarity with the materials and techniques, desirable properties of the gas sensors, and the effect of dopings in that, how these are fabricated, how the technology development is done in that, gas sensing measurements, result discussions, and conclusion. So here one can see that when there is a change in temperature, pressure, humidity, or the particulate matter, or biosensing or gas sensing is to be done, there can be a signal, electrical signal, which can give an output directly or indirectly to give a state which is 1. It means that presence of a gas, and 0 when there is no gas. But intermediate thing can be a linear response, that when the concentration of the gas is changing, it is changing in a particular range, it is changing, giving us a linear response. So we would be interested to know what are the salient features, what are the requirements of, I can skip this slide because I have already told that for the air quality monitoring or for environmental monitoring for these particular gases, we can use these gas sensors. Other than that, they have got applications in domestic uses, industrial uses, and also in the food quality measurement. So what are the working principles or the technique used? Like in the case of adsorption of a gas or a liquid analyte, there may be a change, which is a change in resistance, or there can be a change in the in the capacitance. So depending upon what type of application we are using, here we will restrict ourselves to chemical sensors. And chemical sensors would mean that when there is a change in the say analyte concentration, there is a change in the resistance of the sample, and that is basically quantified. So the selection criteria would be the cost of a sensor is is also a very important parameter, that it should be inexpensive, the life, that how much cycles it can endure, sensitivity, cross sensitivity, robustness and scalability, response and recovery time. We would these are the some of the parameters on which the designing of the gas sensors or the testing is done. So when we are talking about their emergence, this is a brief timeline that in the year 1923, first catalytic gas sensor, which was a platinum, but it was requiring a high power, high temperature. These were the issues. These have evolved over the years, and now with the help of nanomaterials and with the advent of many synthetic routes and techniques, now there is a changeover from the one which was long back, which was the historical, to the semiconducting oxide, and there are number of materials which are being used, and nanotechnology is being employed to for the tailoring or the tuning the properties of these sensors. So this sensor, this material, chromium oxide doped with a titanium, was commercialized by Captor Science Sensors Limited, UK, which was a P-type of a sensor. So we here need to understand what is an N-type and a P-type of a sensor, and how do they respond to different oxidizing and reducing gases. So materials and synthesis routes also play an important role. If we are talking about semiconducting oxides, then these can be synthesized in the form of, say, pellets, thick films, and thin films as well. Whereas conducting polymers, and there are, if we try to make other techniques like thick films using taking the powder and then solution casting them, and also the thin film electrochemical methods, then these can be in the form of thin films. And different techniques, like if we are talking about thick films and pellet, then solid state route and the co-precipitation route can be used. But here the co-precipitation route can be tailored to make the material in the nano range. So depending upon what type of material synthesis we are using, we can adopt these methods in order to prepare the material, and which can be converted to a gas sensing setup. Actually, I'm just rushing up now because otherwise this gas sensing part itself would take more than an hour or so. So, but I would just like to give you a flavor of this, so that what kind of research and how it is done is actually can be illustrated by these. So the desirable properties of a gas sensors are, we would need a high sensitivity and high selectivity, least cross sensitivity, fast response and recovery time. Reproducibility is also one of the factor, because if it is not reproducible, then in that case the response will vary from time to time, and which is also again not desirable. And the linear response in a desirable range, that will help us in quantification, that if we, this much is the ppm of the gas and this much is the resistance, if we can say tailor make that response by quantifying in some mathematical form or in other phase. And the detection limit, each gas has got a detection limit, is important for each gas identification. So these are some of the desirable parameters which are needed for a gas sensor. And the selection of material would mean that either it can be a metal oxide semiconductor, which are inherently gas sensor, but they show sensitivity to many gases, which is not desirable. So one has to make them selective by different other methods, or one has to tailor make or try to study the doping effects in that, so that they can be sensitive to a particular gas. And the and enhancement in those cases, enhancement in selectivity is also done by using different filters. And are there other methods which can induce or which can enhance or make a gas sensor selective? For this case, doping has been done in different materials to tailor make their properties for a specific gas. So if we try to see the effect of doping, then the choice of dopant plays an important role. When we talk about choice of dopant, it is also important how much amount of dopant is there, and again, in which range it is giving us a linear response. So changes in structural properties are studied as a function of doping, morphological changes are studied, their change in the electrical properties, and the gas sensing response, undoped versus doped is studied, and then one does the modeling of the gas response, that effect of temperature and many other things are incorporated into that, and the surface effects are also taken into care in order to see the effect of the doping on different gas sensors. So here, selection criteria, suppose I am choosing a gas sensor which is a resistive chemical sensor. The material can be a semiconducting oxide. The nature of dopant and doping level has to be studied, and method of preparation can be a solid state route or a co-precipitation route, and the sensing material could be iron oxide doped with titanium or zinc oxide powders doped with different other dopants. So if we try to understand this, I can skip this synthesis part, but I would be keen to show you that how the quantification of the structural and many other properties is done. So if I take this case of, say, this is a case of ZNO. First, the material is synthesized in the undoped form, and then a selective amount of doping is done. And so here the nature of dopant is chosen, as well as the amount of doping is also chosen, so that it can show up enhancement in the gas sensing properties. But it is not that you will choose any dopant and it will show an enhancement. It may not show any effect. It may show a very reduced effect. So in that case, the research work is concentrated on choosing and tailoring the properties which can enhance the gas sensing property to a particular gas of a particular gas sensor. So here, using the XRD, the phase purity and the crystallite size of the sample is determined. One can see this paper, which is published in Physica Status Solidi A. One can see the ethanol sensing characteristic of this material, which is doped with aluminium and nickel, and co-doping is also done. So here details about the synthesis of the gas sensing material doped with these two dopants is given, and how the tests are done. One can have a look on that. Other paper, in that paper, one can also see this is another paper. One can see the morphological changes occurring as the doping is proceeding. So one would be interested to know if the morphology is changing. This is the case of ZNO. If the morphology is changing from this to this to this to this, then how it is affecting the gas sensing response, how it is affecting the electrical properties, how it can be modeled in terms of a resistance model in which the grain boundary, surface resistance, bulk resistance can be modeled in order to establish the structure property correlation of these sensors. Similar way, one can see the changes in the electrical conductivity and the activation energy, and can try to see what does the porosity of the sample is associated with all these parameters. So one can again see these papers. In this paper is in RSC Advances on enhanced gas sensing performance of indium doped zinc oxide nanopowders. And other than this, the device, I would be now keen to tell that how the device is fabricated. So once we have developed the nanopowder, it is mixed with an organic vehicle, and a homogeneous slurry is formed, which is then screen printed onto the alumina tiles, and the firing is done, and then the very thin wires or in the micron range are used for welding and bonding. For this figure, I would be thankful to the courtesies UCL UK and City Technology, which had provided us with these IDTs on which we had coated our material and screen printed our material for the gas testing tests. So one can see this is the actual configuration on the alumina. One can see the screen printed sensor which is there on this, and this is on an IDT. IDTs are used for making the contacts on the top, and underneath. This is a platinum track which is underneath the IDT in order to heat, and this is powered by another circuit which can change the temperature of the sensors in a range of, say, it can go from room temperature to 600 degrees Celsius. And on the top, these are the gold IDTs which are used for making electrical connections. So one can, this is the gas sensing test, which is done with the help of, so gas sensing test would mean that we are able to quantify the resistance change with the change in the concentration of the gas, which is aided, and we also change the operating temperature and the concentration of the gas in order to establish that if in what range the gas response is linear and how the performance is changing as we are going from undoped sample to a particular doped sample. And we use mass flow controllers for that. And so the gas testing test would tell us that the sensor is subjected to analyte gas at elevated temperatures, whether there is an increase or decrease of a resistance is occurring with a particular gas, what is the optimum range of operation, and then we check the response at different temperatures. Also, for the real-time test, the humidity interference is also studied, because the real life, it is assumed that we can take the humidity level to be 50%, but one studies these from, say, varying the RH from 10 to 90, and then tries to see that whether the sensor response here would mean the resistance. If I'm talking about the resistive sensors, whether the response is a function of humidity or not, and then the effect of dopants and doping levels are quantified. So here one can see here that...
sorry to interrupt you, ma'am. Can you please conclude your talk?
Yes, sure. So this is a N-type response, and so there is a resistance decrease. And these are examples of other N-type and P-type of sensors. And these are the responses without the gas, and this is in the presence of gas. One can see the resistance change. And the modeling is done onto these sensors in order to establish and tailor make their properties. So I can just skip all this. Just a moment. So the conclusion could be that more and more advancement can be done for optimizing these responses for a higher level. And there is a lot of scope of this future work. One can study different dopants, one can try different synthesis methods, and one can try to model these for predictive measurements. And so the way forward would mean that we can all work at an individual level as well as at the research level in order to make our environment a place where we can mitigate these effects, and we can use with the advent of technology, we can try to orient our research which is towards the societal thing. So in this case, this is an example of a penny farthing cycle, which would say that the consequences and the efforts have to be equalized or balanced in order to bring the positive change in the society. And we have to have a comprehensive holistic approach which is needed. So with that, I would like to thank all my collaborators for the UGC UKD project, Professor Ivan Parking, late Dr. Russell Binians, Professor David William, Dr. David Pook, Dr. Anita, and Dr. Sachin, and Dr. Neha from my lab, and are all past and present principals of Gagi College, University Science Instrumentation Center, and Star College and UGC UKD thematic grant. And I'm thankful to the organizers for giving me with this opportunity. Thank you very much.
Thank you, ma'am, for this wonderful talk. We have one question from Warren Rosario. Please.
Just a moment. I just come back. Just a moment.
Lecture. What is your opinion on using biological elements along with nanomaterials for increasing the selectivity of a sensor towards a particular gas?
In that case, firstly, one has to see, one has to optimize, one has to study their individual effects first, and then one can do the combination and can try to use that. I myself have not used any biological entity, but we had synthesized nanoparticles using plant extracts and other things, so that can be done. So I hope that these trials can be done and literature can be studied, and in case some positive effect comes, it can be used.
Okay. Thank you, ma'am. Is there any other question from the panelists?
Thank you, Dr. Vanna, for such an insightful talk. I think most of the participants must have enjoyed and being interactive. The topic selected was most appropriate for our theme of the workshop. Now, I know that you've been working on gas sensors, and this time you did not discuss much of your work, but I would, since I follow your work, so I know, so I would like to tell the audiences that yes, ma'am, she works a lot on nanosensors. She'd been working for several years now, more than 20 years she'd been working. So if anybody is having any query related to gas sensor, so they can put the questions to her through email. So, yes, right?
Thank you so much. Thank you all the organizers for giving me this opportunity, and I would be happy to share whatsoever I know. Thank you very much.
Thank you, ma'am, for sharing your reflective knowledge with us. Your session was full of passion and priceless knowledge of our current environmental problems. Detailed case study and survey presented by you will give us a starting point to our young scientists and researchers. I'm sure that your insight on the potential solution to climate gravitation will encourage the participant to pursue research in this area. Thank you so much, ma'am, for the wonderful talk.
Yeah, thank you very much. Yeah, thank you very much for the opportunity. Thank you very much.
Thank you, ma'am. Shilika, can you please invite our next speaker?
Thank you, ma'am. Our next speakers are young researchers from our institution, and they will be talking about the application of nanomaterials in biomedical application and as an energy sources. First of all, I would like to invite Ms. Kirti Saxena. She is currently women scientist at AINT, Amity University, Noida. She did her master's in biotechnology from Agra University. Her research interests are currently focused on nanotechnology and biosensor technology in cancer and H. pylori detection. She has more than 15 publications till date with H index of 9. Today's title of her talk is Development of Electrochemical Biosensor for Detection of H. pylori Specific Toxins. Kirti, over to you.
Thank you, Shankika. I hope my slide is visible.
Not yet, Kirti.
I have already shared my screen.
Can you reshare your presentation?
I will. Now is it visible?
No, Kirti. Can you stop share and then reshare your slides?
Yeah, I am doing.
Hello, Kirti. Hello. Um, Can we move to next participant, Pooja
Yes,
Bhattacharya?
Shikika. Please call the next speaker.
Pooja,
Yes, Sangeeta.
are you there?
Hello.
Hello, yes, Pooja. Can you share your presentation?
Yes.
Please share it. Ms. Pooja Bhattacharya is pursuing her PhD from AINT, Amity University of Noida. She did her bachelor's in electronics and communication engineering. She received her master's degree in nanotechnology from Jadavpur University. Her current research interest is on wastewater remediation, antibiotic remediation, porous nanomaterial, metal organic framework, semiconductor nanomaterial. She has published her research paper in highly reputed journals. Her current topic of talk is metal organic framework in wastewater treatment.
Is it visible?
No. Please share your presentation.
1 minute. Is it visible now?
Yes, Pooja. Put it on slideshow mode.
Yeah, 1 minute.
Yes, Pooja, it is visible. You can see.
Good afternoon, everyone. I am Pooja Bhattacharya, PhD scholar in Amity Institute of Nanotechnology, Amity University, Uttar Pradesh. I am working under Dr. Sandeep Chakraborty and external co-guide is Professor Dipankar Bandyopadhyay, IIT Guwahati. My topic of this talk is metal organic framework in wastewater treatment. First of all, let us thankful that we can get a clean, hygienic water, where not all people have this opportunity. So what is the background? Why we need wastewater treatment? Because there is some contaminants that can contaminate the water that we are using. So the water becomes unusable. Now, for my work, I have chosen the pharmaceutical contaminants. So where these pharmaceutical contaminants come, 30 to 90% antibiotics can be flushed into the environment by our household and human resources. Others are animal antibiotics, as well as there is some industry use that can be also flushed into the system. And as a result, that can generate multi-drug resistance bacteria. India and China has the highest antibiotic population so far. So why we need new kind of wastewater treatment? Because the usual wastewater treatment is not very much effective against this type of contaminants. So what we have so far, that is the sedimentation technique, filtration technique, disinfection technique. In the sedimentation technique, in general, it acts for the heavy material, where the heavy particles sediment into the water, and that's we can treatment the water. For filtration technique, we use some kind of filter, but if we have very small particle that can go through this type of filter. And for disinfection, that can actually cure the biological contaminants like bacteria and others, but it is not effective for chemical and pharmaceutical contaminants. So two types of schemes can be used for this treatment, that is adsorption and photocatalysis. For adsorption, we use some kind of porous material that is adsorbent, and that can adsorb the pharmaceuticals from the water and can remove the pharmaceuticals from the water. As well as for photocatalysis, we use a light source where the pharmaceuticals can be degraded into intermediate products and carbon dioxide and H2O. Now, for my PhD work, I have chosen antibiotic removal by adsorption. For this, I have jotted down that
number of publication in recent years is exponentially rising. That means the dire need of this kind of work is understandable for everyone. That so that in recent years there's so much publication in antibiotic treatment. So why adsorption? Why not other method? Because it is easy to handle, as well as no extra circuitry is required, as well as it is cost effective, and it can be used for large scale. What kind of material we can use for water treatment? That is material with high surface area and good surface properties, and the material that we can be reused, means easy removal from the slurry, and that material can be reused further. So this is now 1 minute. My material is metal organic framework. What is metal organic framework? Metal organic framework has two type of things, that is metal ion, that is connected by organic linkers. Here I have given a simplified look of a metal organic framework. It has a cage-like structure where the nodes are metal, and that is connected by each other by a organic linker. Now we can change this organic linker as by our use, and that's why we can get the control geometry. So what are the different type of properties we get for metal organic framework? That is the tunable structure, open channels, high surface area because of this cage-like structure, and control geometry because we can control the metal node as well as the organic linker in the system. Why ZIF? ZIF is a very well-known metal organic framework, that is zeolitic imidazolate framework we use in the system. It is quite similar than as the zeolites. That is a natural compound. So the distance between the inorganic nodes in zeolite is 3 angstrom, where in ZIF it is double of that, that is 6 angstrom. Much higher. So we can get a much more pore diameter in the ZIF network, as well as it is not that rigid like zeolite structure, and it can also have the flexibility in the pore size for use of these organic linkers. We have used wet chemical technique where we have mixed the different type of metal salts with the imidazole and we used a wet chemical technique where we can synthesize the ZIF structure, and by heat treatment in controlled atmosphere we can get the porous nanostructure from the material. These are the optical image of the MOF as well as XRD, where the figure A shows the XRD of the ZIF MOF, which shows it completely matches with the simulated data, showing that phase period ZIF 67 has been formed and it is crystalline. From this XRD we can see. Now we have heat treated the sample in the controlled atmosphere, which shows that some amorphous nature in the structure. There is some peaks for cobalt oxide as well as cobalt, and there is some amorphous peaks of carbon as well. So the picture C shows the morphology of the crystalline ZIF, and by heat treated it we can get this kind of coral-like porous structure, which is a mixture of cobalt oxide, cobalt as well as carbon. Now we have done the XPS analysis of the sample, which completely shows it contains the carbon, nitrogen, and abundant amount of cobalt. Now, what kind of cobalt is in there? Is it cobalt 2, 3, or 0? So the analysis of the data shows that it has 3 kinds of cobalt: cobalt 0, cobalt 3, and cobalt 2 in the structure, which actually is beneficial for the adsorption of the sample. So the properties of the sample, that is property of the material, I have also done the Raman analysis of the sample, which shows two peaks at D and G peaks that shows the graphitic-like carbon nature of the sample, and the right-hand side picture shows the TEM image of the sample, which shows some tubular CNT-like structure in the sample along with the porous nanostructure in the ZIF67 sample. This is the antibiotic removal of the MOF. The first picture shows the final concentration with a time graph, which shows that final concentration decreases gradually with time, which shows the good antibiotic removal property of the sample. The second picture actually shows the reusability of the samples, that it can be reused. It can be reused properly. That after fourth run, it is also only 8% of the removal percentage has been decreased. So that material is very much reusable. Now, how can we collect the sample? Because of the cobalt in the sample, it shows excellent magnetic property. So the third picture shows that the material can be removed from the sample completely by an usage of the external magnet. And we have also done some antibiotic removal for 4 different kind of antibiotic, which shows excellent results. Future scope of the MOF plate structure. Now we have changed the ZIF67 to ZIF8 as well as bimetallic, which contains ZIF67 as well as ZIF8, where it shows that with changing of the metal nodes, the antibiotic removal property is also changing. The removal percentage is also changing. That shows the removal percentage completely depends upon the metal nodes of the structure. This is an interesting property, and we can have different type of nano composite with the MOF for usage of different type of adsorption property. MOF derivative can be used for wastewater treatment. Bimetallic MOF is a good option for this, and we can use careful selection of MOF can be used for the photocatalyst also. I would like to thank my supervisor, that is Dr. S. Chakrabarty, and external co-guide Professor Dipankar Bandyopadhyay for their guidance, and Amity University for giving me this opportunity. And I would also like to thank UGC DAE CSR for funding support. Thank you.
Thank you, Pooja. Is there any question for from the participants or the panelists? I guess there is no other question. So thank you, Pooja. Hello.
Yeah, hi.
Yes, Pooja.
Thank you.
Our next speaker is Mr. Rohit Sharma. Rohit, are you there? Rohit? Okay, Kirti, are you there? Can you share your PPT now? Kirti? Rohit Sharma? Chinmay, are you there?
Hello.
Yes. Chinmay?
Yeah, I'll just present. Just a minute.
Okay. So here Chinmay Shukla is our next speaker. He is final year student of integrated MTech from our institution at MIT University, Noida. His research interests include 2D materials, thin film, photocatalysis, and DFT-based simulation of materials. He has also won the 4-minute research pitch national conference for the undergraduate category on the topic of low-cost optimizable process for effective 2D and 3D heterojunction creation as a basis for the hydrogen generation, organized by the IIS Jaipur and Government Madhav Science PG College, Ujjain. His topic for today's talk is nanostructured semiconductor-based heterojunctions for water splitting towards S2 generation. Over to you, Chinmay.
Thank you very much. Share. Okay, so my screen is visible, right?
Yes, it is visible.
Okay, thank you. Okay, so my topic for today will be nanostructured semiconductor-based heterojunctions for water splitting towards hydrogen generation. So this topic will be based upon what are heterojunctions and why do we need heterojunctions, and I have included some of them which I had previously to show the need and the helpfulness of heterojunctions. So,
next मैं एक बार टॉप मैं कुछ नहीं पढ़ा भगवान टॉप नाम पे
yeah, okay. So water splitting. So we need to first understand the mechanism behind the splitting of water. So the mechanism behind splitting of water is when light is shown upon. Yes, ma'am.
Yeah, your volume is very low.
You can't hear me. Okay. Hello, am I audible?
Chinmay, we are unable to hear you.
Hello. Now is it better?
Yes, yes. Please.
Okay, okay. Okay. So first we need to understand the mechanism behind splitting of water. So when a light is shown upon a photoactive semiconductor, there are excitons being generated, that is electron and hole pair. And these electron and hole pairs, they move and create the hydrogen gas and the oxygen gas by the means of reduction and oxidation reactions. So to effectively split water, we need 4 electrons and 4 holes. Now, the place where heterojunction comes into play is every point of contact. So, a contact can be with the electrolyte, contact can be with the bottom electrode, contact can be with another semiconductor in the photoactive material, and the contact can be with the metal and electrolyte. Now, moving on, the heterojunction uses. So, why do we use heterojunction? So, firstly, it is to curtail the amount of recombination that is happening. So we have heard about this term where the electrons fall back to the valence band and create recombination. So these recombinations are just wastages of the electron and hole pairs that were generated by the photons instead of them being used inside the reaction. So to avoid this, we create a charge transfer mechanism by the means of heterojunction with another semiconductor material or a conductive polymer or graphene layer or maybe a metal contact. So this is one of the uses. Second use is the protective layer. So what happens is because these materials are nanomaterials and they are very active in nature, so the corrosion is a big problem with them. As the environment is very, it has some electrolytes in it. So this to protect them, we add a protective layer. For example, TiO2 is added onto a gallium arsenide platinum structure, and then it can also be used as a support layer. So when we are using a 2D material, 0D material, or a 1D material, they require certain kinds of supports. So this support brings in the heterojunction concept, where two different kinds of material they are in contact. So this is also one of the reasons where the heterojunction comes into play as a support layer, and then it can be as a co-catalyst or a dye or a quantum dot kind of a structure, which can help in increasing the overall absorption. So now we move on to the concept of band bending. Now, when we talk about heterojunctions, there is this concept of band bending occurring. So when there are two different Fermi levels that are mismatched, okay, the Fermi levels aren't aligned. They have a certain difference in them. So what happens is when they are in contact, the electrons either flow from the so the electrons basically flow from the higher uh, Fermi level to the lower Fermi level, or the lesser work function to the higher work function, so that they can effectively come together, and the vacuums can be aligned. Now this creates an offset. This Fermi level alignment creates an offset. This offset is noted as the VBB over here, which is there for both the cases, where on the right the semiconductor has a higher work function than the metal, and on the left hand side the metal has a higher function than the semiconductor. So these create depletion and accumulation layer. So these layers they can help in accelerating the charges, and these can be sometimes helpful, and sometimes they might create a trap side. So now moving on, we need to understand the types of heterojunction. So the most useful heterojunction is the type 2 heterojunction, wherein the electrons, the conduction bands are aligned of. So for example, a material A has the semiconductor has a higher conduction band than the material B, and the valence band is also higher. So the electrons, they move in the direction from the higher conduction band to the lower, and the holes, they move in the opposite direction. So this way, the electrons and holes, they are effectively separated, and the recombination decreases. The other heterojunctions are due to different materials or multiple junctions like barriers and wells. So moving on, now we need to understand the most important concept of band alignment. So the materials I have shown here is bismuth ferrite and molybdenum sulfide. So the band edge positions, this signifies the conduction band, and this signifies the valence band. And the green lines signify over here the potential for splitting water. So the conduction band for MOS2 lies over here, and the valence band lies over here. And similarly, if you can see for bismuth ferrite as well. So molybdenum sulfide is known to be a good hole transport layer. So over here, my concept of using molybdenum sulfide is as a whole transport layer, and bismuth ferrite as a support, plus using it for electron transport. Now moving on, this is the XRD diagrams. So the XRD, so I have experimentally synthesized bismuth ferrite and molybdenum sulfide using spray pyrolysis. So there are different time scales on which I have sprayed them. So the molybdenum sulfide is being varied from 60 seconds to 90 seconds, and bismuth ferrite is kept constant at 80 seconds. So bismuth ferrite XRD, you can see that the peaks are with respect to bismuth ferrite, and for molybdenum sulfide they are with respect to molybdenum sulfide. But the interesting phenomena is when they are sprayed on top of each other, and a heterojunction is being created. For the 60 second, you can see that bismuth ferrite is more dominative than molybdenum sulfide. The peaks of bismuth ferrite are more dominative, and if you can see the variation and changes from 60 to 90 seconds, you can see that bismuth ferrite and molybdenum sulfide now have a much more even distribution of their peaks for the 90 second, which means the junction is being created which is not dominated by one of the materials. It is a very suitable junction now. Now, why is this important? This is important because we will see the changes in the overall photocurrent. So before we move on to the photocurrent, we need to see about the photoactivity. So over here is the UV visible plot and the tau plot. So the UV visible plot helps us to see that the molybdenum sulfide, which is over here, has a low absorption rate than the compared junctions. So the bismuth ferrite helps in increasing the total absorbance. And you can see one more thing over here, that the band gap first starts to increase when the junctions aren't evenly matched. The band gap starts to increase, and when the junctions are evenly matched, it starts to decrease. And this will play a role when we see the photocurrent efficiencies and the overall photocurrent that is being produced. So this is the current versus voltage statistics. So over here you can see that when the junction is made very well, the amount of current that we obtained is 0.76 milliamperes for the bismuth ferrite and the molybdenum sulfide, 90 seconds spray time. So this only occurs, and it occurs only at a minus 0.22 volt over potential. So which is a very good thing. So here we need to understand two things. First, why there is a lower photocurrent for the lower spray time materials. So first thing is the absorbance. So the thickness plays a very important role. When the thickness is lower, the amount of light being absorbed is also lower. So in the nanomaterials, the thickness plays a very important role. Now, but the thickness is also related to the conduction of electrons and holes. So this is also one thing where we need to optimize both the thickness with respect to the absorbance and thickness with respect to the conduction. And when we do that, we will get what is most desirable and most necessary, which we saw in the case for the 90 second, which we have a 0.76 milliampere. Now, these are some DFT results that I had obtained. So these DFT results are important to understand how the atoms actually play a role. So the PDOS is partial density of states. So over here you can see these are the schematics of two heterojunctions being created. One with 2D zinc oxide and Cu2O111, and the other one being with GC3N4 and Cu2O. So why is this important? Because you see the distribution of the atoms and their states over Cu2O, and you see that for similarly ZNO and GC3N4. But when they will be created in a heterojunction, there will be hybridization of states, and this hybridization of states can help in generating a better response when light is being shined upon it. So this can also be seen with the help of work function. So work function is basically the value of Fermi level minus that of the vacuum. So what essentially it means is the amount of energy required for an electron to be free. So when there is light being shined upon any semiconductor material, the electron moves up to the conduction band, but then to make the electron free, extra energy is being required. So that extra energy we have to supply, and now to reduce that extra energy to make that electron free, we create a heterojunction. So on the right, you can see the work function for Cu2O calculated is 11.39 eV. But on the left, you can see for ZNO being 5.91 only, and for GC3N4 even lesser, 4.80. So now when they will be in contact with Cu2O, they will bring down the overall work function, as we saw in the band bending case, because there will be movement of charges. Now to see them in the place, so over here you can see MOS2 and C3N4. This is a person's work. So what the researcher did was they first calculated the V effective for the individual layers, and before relaxing them and creating a heterojunction, and then after relaxation they saw it. So what you can see over here is the flat edges are of the vacuum levels, and the ones which are down are of the elements. So for sulfur and molybdenum, you can see this kind of a pattern. And for the case of C3N4, because it is a planar 2D structure, and thus it has just one dip. So but over here, when they are relaxed and a heterojunction is being created, so when the relaxation happens, what happens is the electrons essentially move, the charge transfer happens between them. So there will be certain charges moving from the molybdenum sulfide to C3N4 because of the lower work function. So the molybdenum sulfide will supply its electrons to the C3N4 material because of it having a higher work function. and this supply is being seen in the red isosurfaces. So these isosurfaces depict the amount of charge being transferred. So the green ones depict the recombination and the charge transfer from C3 and 4, and the red ones depict the electrons being transferred from MOS2. So you can essentially see how when the heterojunction is created, there is a charge transfer happening, and how this will be beneficial for accelerating the electrons further when the light is shown. So thank you very much, and I would like to acknowledge and thank my guide, Dr. Sumant Upadhyay, Dr. Ranu ma'am, for helping me with this opportunity to present, and Dr. Opesina for always being there for us. So thank you very much. So any questions? Please do let me know.
Chinmay,
yes, sir.
Good work. Good work. In one of the slide, you have shown that you have the pre-pattern surface on the gallium arsenide.
Yeah, just a second. I'll just. Yes, sir.
This is the simulation statement, simulative statement, or this is the experimental
Sir,
statement?
this is just a pictorial diagram to show how
I just wanted to know, you are claiming experimentally this fact, or you are just simulating this fact?
So which one? The one on the left?
This pattern gallium arsenide.
No, so this is somebody else's work. I've just used it as a reference to define the heterojunction use.
See, gallium arsenide, do you know why the gallium, being one of the best material for optoelectronics application, having the band gap in the NIR region and the electron mobility of 8,800 millivolts per second, even means this material was not fulfill the expectation of the science community.
Right, sir.
The reason was very simple, that you cannot get 50-50 or 1:1 gallium arsenide surface. Either it will be gallium rich or it will be arsenic rich.
Right, sir.
So in that case, if you are looking for the gallium pattern, gallium arsenide, it seems to be not possible, because it will be not either it will be gallium pattern surface, or it will be arsenic pattern surface, or it will be some discrepancy will be there. And if you are putting over the platinum interface, due to the change in the ratio of the gallium and the arsenic, right? So
yes,
your function will be different, because if you take the gallium rich, the function will be different. If you take the arsenic rich, the function will be different.
Right, sir. Absolutely.
So you need to see, when we are talking about this kind of the statement, see, for getting the publication nowadays, means you are in the open essays, you are in the anything. Getting publication is not a tough task. People called nowadays, even the graphite has been given the new name of the multi-layer graphene. You can't stop the people to go for the fancy word.
Right, sir.
But when I really want to do some scientific work, please be careful for all this stuff, because gallium arsenide not a very good materials with the band gap 1.4 eV, and with the schematic problem is lot of schematic problem with your gallium arsenide.
Sure, sir.
Okay, thank you, Chinmay. Now I am calling to our next speaker, Rohit. Are you there? Chinmay,
yes,
can you please unshare your screen?
Yes, ma'am. Just a second.
Okay, Mr. Rohit Sharma, PhD scholar. He's the PhD scholar in our MIT Institute of Nanotechnology. Rohit Sharma had completed his BSc honor in physics from Atmaram Sanatan Dhan College, University of Delhi, and MSc honor in physics from Central University of Punjab, Haryana. He has published 10 papers and attended many national and international workshops and conferences. The title of his today's talk is 2D TMDS for electronic applications. Rohit, yes.
My slide is visible.
Yes, your slide is visible. Now you can start.
So good evening, everyone. I'm very thankful to Dr. Nidhi Chauhan and Dr. Ranu Nayak and the whole organizing team for giving me an opportunity to present my work in this value-added workshop, Smart Nanotechnology for Societal Application. The title of my talk is 2D Transition Metal Dichalcogenides Material for Nanoelectronic Applications. So in this talk, I'm going to discuss about the photodiodic application of molybdenum sulfide. So the outline of my presentation is introduction, synthesis of 2D materials, liquid phase exfoliation of 2D MOS2 and its photoresponsive behavior, and the future scope of these 2D material applications. So basically, photodiodes is an optoelectronic devices that converts the incident light or photon into the electrical signals, in which when a incident light basically falls on a semiconductor material, the electron hole pair is generated and this is converted into the electrical signal. This basically photodiodes have an application in the health sectors, from optical spectroscopy, sensing applications, and the sanitization application. So why I'm working on 2D materials? 2D materials basically explode from graphene, but the graphene has a disadvantage that it doesn't have a band gap. So our group is basically working on MOS2, WS2, WSE2 and MOSE2. These materials have basically advantages, and one can see as the number of publications by looking picture B. Till 2020, more than 25,000 papers have been published in the graphene, or I can say more or larger paper has been published. The second next explored material is molybdenum sulfide. So the molybdenum sulfide has a basic variety of properties, and 2D material, from the figure C, you can check that 2D materials basically covers the entire visible and UV region from hexaboron nitride to the graphene. And these all the 2D materials are from insulated to the semi-metallic in nature. Whereas some phase of the 2D material is basically having a metallic phase. So the 2D materials having a MX2 type of structure, whereas a single metal transition atom is sandwiched between the two chalcogen atoms, and they have a superior optical and electrical properties such that their band gap has been transit from indirect to direct band gap as the number of layers is reduced. They have a very moderate mobility compared to the graphene. The thermal stability is higher, up to 1100 degrees Celsius in the atmosphere. I'm here talking about only an MOS2. Whereas the figure 3 shows the structure of MOS2 and WS2. These they have basically a two structure. One is hexagonal structure and another is trigonal structure. Hexagonal structure is where the stacking is different, and the side view of this 2D structure is shown over here. The synthesis process of 2D material is basically there's a top-down approach and bottom-up approach by which you can synthesize your 2D materials. In the top-down approach, we have the bulk material and we will exfoliate. This exfoliation can be done either by mechanical exfoliation, liquid phase exfoliation, or ion intercalation. So the ion intercalation and mechanical exfoliation has a drawback because mechanical exfoliation cannot be a scalable process. There is an ion intercalation in which we have a lithium ion and we intercalate into the bulk material to remove the van der Waals interaction. But this ion interaction basically results into the metallic phase. So this cannot be appropriate for the semiconducting applications, whereas in bottom-up approach, we have some expensive instruments. So basically our group is working on liquid phase exfoliation. So in the upcoming slide, I'm going to show that how, what are the parameters that we have used for liquid phase exfoliation of MOS2. For the liquid phase exfoliation of MOS2, we have purchased a bulk MOS2 from Alpha Azer and then taken an appropriate solvent. Here we have taken 4 solvents, dichlorobenzene, N-methylpyrrolidine, DI water, and dimethylformamide. And these solvents has been taken into 10 mg per ml concentration. Further, this suspension is sonicated for 8 hours and centrifuged at 3000 RPM for 15 minutes for the separation of thinner flakes. And this suspension is basically characterized by the different characterization tools such as FESM, XRD, Raman spectroscopy, and UV visual spectroscopy. So this slide shows the FESM image and AFM image. So morphology and the film nanosheet thickness has been studied by FESM and AFM. Figure A to D basically shows the FESM image. The figure A is for DI water, and the inset shows the cross-sectional image of DI water-based exfoliated MOS2 nanosheets. The figure B shows the DCB-based exfoliation, and we found that this DCB base have a wrinkle-like structure, and this is not appropriately exfoliated, whereas C and D shows a layer-like structure. From all the AFM image, we have found the nanosheet thickness is 5 to 35 nanometer, and the nanosheets are better. The NMP based exfoliated nanosheets have better quality, as we have seen. The layer thickness is from 2 bi-layer to 12 layers. Further, the XRD pattern of different exfoliated DI water, DCB, and NMP DMF based exfoliated MOS2 has been shown. We have found that NMP and DMF based exfoliation have a peak occurred at 14.3 degrees, 3 degree, which belongs to the 002 plane, and the intensity of this peak is reduced, which again suggests this number of layers has been reduced. This reduced number of layers and the Miller plane 002 suggests that it has a semiconducting phase, and the interplanar spacing calculated for this is basically 0.65 nanometer. Further, the optical properties has been studied by the UV vis spectroscopy, and the absorption spectra suggests that there is a 4 peaks occur: A, B, C, and D. The A, B, C basically an indirect excitonic transition at the K point in the Brillouin zone, and C and D belongs to the direct excitonic transition at the M point in the Brillouin zone. The band gap has been calculated using the tau equation, which I have given in the upcoming slide. The band gap varies from 1.6 to 1.78. Again, the NMP based have a higher band gap, which suggests the number of layers has been reduced and the quality of nanosheets has been better in the NMP. And also the yield is better in the N-methyl pyrrolidine based MOS2. Further, the Raman spectroscopy, we have found that there is a 2 mode of vibrations occurred, E1 2G and A1G mode. This E1 2G mode is basically an in-plane vibration of molybdenum, selenium atoms besides the molybdenum atom, and A1G is the out of plane vibration. We have found that the peak is quite broader in the DCB, which is due to the phonon confinement, and the defect states occur in the DCB, and the shape of, we have also seen the shape of in the AFM and FESM, we have also seen that the shape of the nanosheets is different, which suggests that which correlate this broadening. And we have found that the peak frequency difference between this is lesser compared to the bulk. The bulk has a 26 centimeter inverse wave inverse, and we have found that NMP has a lesser 24.7, which again confirm that nanosheets has been reduced. Further, the photoresponsive behavior of this MOS2 nanosheets has been studied. For the study of photoresponsive behavior, the schematic of the photodiode is given in the figure A, and where silicon dioxide is coated with the synthesized MOS2 nanosheets. The thickness of the silicon dioxide is 300 nanometer, and the silver paste has been used as a contact as an electrode material. The 395 nanometer wavelength torch has been used. Its power is 1 watt. So the figure B shows the electrical response, and we have found that the nanosheets have a self-powered behavior. This self-powered behavior is due to the uneven metallization and or the charge accumulated at the electrode, and this resulted into the self-powered behavior. Whereas we found that except for NMP, all the diodes have a negative photoconductivity. This negative photoconductivity is due to the conversion of 2D electrons into the trions, and these trions have higher effective mass. This higher effective mass due to the helical mechanism, this is trapped by the defect states, and this defect states reduce the conductivity, which leads to the negative photoconductivity into the other nanosheets except for NMP. And we have found that a few layer MOS2 have a photoresponsivity of 1.08 into 10 to the power minus 3, which is quite comparable, but this negative photoconductive behavior needs to be investigated. For future scope, we can say the photo response can be tailored over a broad spectrum of UV to IR region by functionalizing the 2D material. The performance of MOS2 photodetectors can be dramatically improved by functionalizing this MOS2 structure by hybrid structures such as quantum dots, the integration of MOS2 with the flexible electronics, or all with the optoelectronic functional devices remain challenging because it's hard to synthesize. The tremendous opportunities existed to explore the other 2D materials. With this, I would like to acknowledge our collaborator, Dr. Ritu Srivastava and her team from CSIR NPL, Dr. Radha Pyari Leshram from DRDO SSPL, UGC DAE CSR, and Mr. Sunil Ojha and his team from IUAC Delhi. With this, I would like to thank you, the organizing team, for giving me an opportunity to present my work here. Questions are welcome. Thank you, ma'am.
Thank you, Rohit, for this wonderful talk. Is there any question from the participants and the panelists? Okay, I guess there is none. So I would like to call our next speaker, Ms. Kirti Saxena. Rohit, can you unmute?
Yeah, sure.
Kirti?
Hi, Shilpa.
Yes, can you share your presentation?
Is it visible?
Not now. Okay, it is visible. Kirti Saxena is a woman scientist in our institution at MIT University, Noida. She did her master's in biotechnology from Agra University. Her interests are currently focused on nanotechnology and biosensor technology in cancer and H. pylori toxins detection. She has published more than 15 publications till date with H index of 9. Her title of talk today is Development of Electrochemical Biosensor for Detection of H. pylori Specific Toxins. Kirti?
Am I audible?
Can you speak louder?
Okay. Good afternoon, everyone. The topic of my talk is development of electrochemical biosensor for detection of H. pylori specific toxins. So the Helicobacter pylori is a spiral-shaped gram-negative bacteria, and it resides in gastric epithelium cells of almost 50% of world population. It is a microaerophilic bacteria, and it approximately 3 micrometer long and 0.5 micrometer in diameter. And it also has multiple flagella for their movement. In gastric epithelial cells, it releases several toxins like Kage, Backe, Bave to survive and establishment of infection in gastric cells. It causes several stomach-related diseases like acute or chronic gastritis in almost 100% patients suffering from H. pylori infection. And other diseases are gastric ulcers, duodenal ulcers, and mild lymphoma. And only 1% patients with chronic infection shows gastric cancer symptoms. And H. pylori infections symptoms are pain in the stomach and decreased appetite, bad taste in the mouth, nausea, etc. So there are several methods to detect the infection of H. pylori. It includes several invasive as well as non-invasive tests like endoscopy, histology, culture, urea breath test, stool antigen test, and antibody-based test. Although there are several conventional methods, but these show some limitations, like the equipments they use are very expensive and require the technically qualified persons, and the sample pre-treatment is also very laborious with long time response. So we choose biosensor for detect the infection of H. pylori. So why choose biosensor? It shows very so much efficiency in detection of infectious diseases. Like biosensors are very sensitive, selective, and easy to handle. They are also in low cost as compared to expensive equipments, and we can easily portable them. So the biosensor consists of 4 components like analytes. They consist of biorecognition elements, transducers, and a signal detector. So the biosensors should be show high specificity and selectivity. They should sufficient sensitivity and resolution, and have sufficient accuracy and repeatability. So in my work, this is the schematic representation of steps involved in development of biosensor. So first I have synthesized some advanced nanomaterials and coated them on bare electrode, which is followed by immobilization of H. pylori valence factors. And after interaction of analytes with the biorecognition element, the generated signals are detected by signal detector. So the methodology involved in my work is the fabrication of antigen antibody based biosensing platform for Vacay toxin of H. pylori detection. So for this, I have choose a gold wire electrode and coated with the GCN and ZNO nanocomposite. And then I have immobilized Vacay specific antibodies on the GCN ZNO coated AU electrode, and then perform electrochemical study for validate fabricated biosensor, and optimized it for several parameters like pH, temperature, and other concentration of antigen. So why nanomaterials I choose in my biosensor? It increased sensitivity of sensor, and it enlargement of operating range of sensor by extension of lower and upper detection limit. It also using fabrication of sensor by simple process and minimize cost. It nanomaterials can also help in fabrication of non-invasive point of care devices. So there are some results of my study. The figure A and B shows the characterization study of our nanocomposite. That is, for first slide, A slide shows the GCN nano sheets, and B slide show the SAM images of stack layer structure of GCN and nanorod of ZNO. In figure C, I have shown the fabrication steps. Here we can see the after the coating of nanomaterial, the current increased significantly, which further decreased after the deposition of antibodies. In figure D, I have used Vacay antigen from the in a linear range of concentration from 0.1 nanogram per ml to 12.8 nanogram per ml. And with the increase of concentration, current was decreased. I have also optimized it for pH, and also check the stability of fabricated biosensor. Sorry. So the conclusion of my study was the developed electrochemical biosensor was highly sensitive and selective for detection of H. pylori toxin Vacay. The immunosensor displayed a lower detection limit with the linear range of 0.1 to 12.8 nanogram per ml. The sensitivity of biosensor was 0.3 milliampere per nanogram per ml, And the GCN and ZNO nanocomposite based biosensing platform could be developed as a point of care device, and it can provide prospective applications in clinical diagnosis of H. pylori. Thank you so much for listening and providing me opportunity for this.
Thank you, Keith. Is there any question from the participants? Is there any question from the faculties? Okay, I guess there is no question. Thank you, Kirti. Can you share your slides? Now I request Nidhi ma'am to conclude today's session. Thank you.
Thank you, Shandika. Thank you all. Thank you very much to all the dignitaries and participants. To conclude today's session, first I would like to thank our director, sir, Professor O.P. Sinha sir, for giving me this opportunity to be a part of this workshop. We surely learned many scientific aspects from the expertise in a different field. In order to summarize today's session, I would like to first thank our first speaker, Dr. Amit Kumar sir, for his wonderful insight on sustainable energy resources. He beautifully explained the concept of polymeric nanoparticles based optoelectronic device with physics-based mechanisms. The second talk was given by Sanjay sir, where he explained the importance of thermoelectric and biopolymer material for supercapacitor applications. He elaborated on the quantum effect of various nanomaterials in electric and optical devices. He also talked about the electron spinning method for nanofiber synthesis and application in supercapacitors. Furthermore, our third speaker, Professor Rohit Srivastava sir, delivered an excellent talk on futuristic alternatives to solar energy and mentioned different nanomaterial for renewable energy sources. His work in direction is very renowned and appreciated by the scientific community. Our last lecture of the pre-lunch session was done by Dr. Sampa Saha, in which she highlighted the issue of conventional method for water remediation. She explained different method for anisotropic colloidal surfactant synthesis, which can also be used or applied in food packaging, drug delivery, and biosynthesis application. In the post-lunch session, first talk was delivered by Vandana ma'am on the topic of potential solution for climate remediation, where she elaborated on various methods for different pollutants removal and purification of environmental resources. At last, I would like to thank all the young achievers from our MIT Institute of Nanotechnology. I highly appreciate their enthusiasm and dedication towards the research. Before concluding today's session, I would like to remind all of you regarding today's assessment for all the talks. Ranu ma'am, can you please share the link?
Yes, I've already shared.
Okay. So please provide your feedback for this workshop. Thank you all.